into the cloud. Questions to the presenters during the presentation in the chat. Okay, so if they're incredibly pressing, we can have the other presenter answering them in the chat. That will make sure that we're streamlining our conversations. You ready?
I think we are.
Then I am looking forward to whatever it is you put together. Please come in and share, and let's see. I'm going to stop my own share.
Okay. Well, good morning, all of you. We will be the first to be presenting, and this is Project Setface. As Felix and I are both interested in behavior, we want to do something related to psychology. But our goal in this minor was to learn coding, and so we tried to combine the two of them. We thought of the idea to create our own code in the form of a Hopfield network that could, in a way, differentiate between facial expressions, namely happy and sad. We chose this form of network because it fixates on patterns, and we came to the conclusion that we could describe these facial expressions as patterns. The other option was a convolutional neural network, but due to the fact that we wanted to work with patterns instead of pixels or pictures, and we created our own training data, and the training data for a convolutional network would exceed what we could make ourselves. We began our sessions with the making of a Hopfield network. Firstly, I will describe what a Hopfield network is. Then we will walk you through a project and show you how the smileys we created could be recognized by the trained network. So our Hopfield network starts off in a random binary form and memorizes the input that it receives. The input we used is various matrices in the form of smileys, and they will be flattened to show vectors, because vectors are what is put into the network. We will show you this in a minute. It is a recurrent neural network where all nodes are connected, and there are connections between different layers of the neurons. Important for our project is the fact that we work with one-shot learning, meaning the smileys are presented only once, and there is no need for training it over and over again, so give the same input. This training leads to an attractor state, our network, which means that a pattern that is trained and where the network will go towards it will go towards what we tested it with, what we trained it with. This will get clear to you once we walk you through it. Just our goal with this project is to give a better understanding in how the training of a Hopfield network goes, and just to show you what will come out. So to start off, we will run the initialization, which is required to begin the project. And we begin with creating loads of smileys. Purple is my favorite color, and it will show you, so don't worry. We started off with making the smileys ourselves by hand with all the ones and the minus ones. Those are 15 rows of cells, 15 numbers each. The method to so the output this gives is one of the smileys, and we made 10 of them. To use them, we had to flatten them, which is the first method to create a vector. As you can see, these are the first 10 sad faces, one of which will be, well, we can vary between the number, but to start off, one of each will, one of the sad smileys will be the trained version, so will be put in the network as training, and the rest will be shown as a testing mechanism. Next to that, we defined happy smileys, also 10 rows with the flattening. And last, we created distorted smileys to really test our network. These smileys are ugly, but the first four are the first four are supposed to be happy-ish, and the last four are supposed to be sad-ish. But this should test our network that if it could still recognize the sad or the happy in the faces, then we would be proud of our network. And this is the second method, which is a way harder to work with. It's all the numbers in just one cell. The advantage is that you don't need to flatten it anymore, but it's very hard to see where you change your 1 into a -1. Felix will continue on with part of the training.
Okay. So as Julian explained, we've designed our own smileys with different types of mouths and different types of eyes. In our initial training set, this is the code for the training, we both decided that the happy, the list of happy smileys, H1 flat to H10 flat, and the same goes for the sad list. We did this so it makes it easier to quickly change around our training data. So, and if we look here, H1 and sad1, so sad2 are the most basic smileys we have for both. So in our original training, we used just those two. And I'll show you that we'll run this.
One more bracket.
I see.
And happy list 1 is as you can see H2 flat, which is the second phase.
Yeah, because Python works from 0 to 9.
It's annoying. It starts with 0.
Then here we have the weight matrix. We start with a random initial matrix, and you can clearly see that it's being trained. Although in the end, you'll see here, and once we do more trainings with more smileys, these lines will get more solid. Like it's still pretty blurry. Then we're testing it. And what we did here, this is the test code. And here we said we're testing it with all these smileys. So happy 0, we're skipping happy 1 because that's what we've trained it with. Same here with the sad ones, and here with all the distorted ones, to see if our network can classify it correctly. Also, quickly, the first 4 are supposed to be happy, and the last 4 are supposed to be sad, because it's important to see if our network can actually classify those correctly. Here, it shows us the time step of 1 smiley. Here we have D4, but since let's make this H1 flat.
You need to type in happy.
Was it happy here?
Happy 1 or happy, whatever you want.
Here you can see, since we trained the network correctly, it almost instantly recognizes it. And this is how, like, the state basically, because we've put 10 time steps, so it tries to fit it as well as it can over 10 time steps. But since the happy is a very simple one, it gets it right almost immediately. Here we've plotted the final state of all our smileys. So these are the 9 happy ones, which our network correctly is able to reach. The 9 sad ones, he's also able to correctly reach. The distorted happy ones, he's kind of getting it right. But now it's like, we can look at this, but we could also make an actual classification program. So we've coded a quick feed-forward neural network where we've set a threshold of 209, because the total, we have 15 by 15 matrices. So in total, there's 225. So we're allowing it to make 16 mistakes, because the smiley is like 25 pixels. And then if we run this and we do the recognition, with happy, it says he has those correct, and then the last ones are all false. And then we also had the confusion matrix, which shows that exactly. Okay. Now Julian will go over what happens if we use different initial training data.
Okay, so there are various types of training you could use. You could, for instance, try it with only a happy smiley. We will not do that, but the outcome with only one happy smiley would be that, with two happy smileys, I mean, so happy 1 and happy 0 would be that all the smileys that you put in will get to the attractor state of happy. So it's actually, it will not differentiate between any smiley at all. It will just be happy all over the place. What we can add now is the sad list 0 and the happy list 3. So just remove the 2 brackets and the, okay.
You said add, right?
Yeah,
Sad
but
list,
could remove the comment, but it's no biggie.
Oh yeah.
No biggie. And what we found very interesting was that this order, so happy, sad, sad, happy, or any order of the 4 made a huge difference in the understanding of our network. Okay, so the weight matrix is still a little bit of blurry, but you can see clear connections between the neurons that are important for the network. This will be the testing with the same states. Yes, and this is the time step of happy 1. Let's go to distorted 1. So just D1. Okay, so this is supposed to be a happy face. It's supposed to, oh no, okay.
I double clicked.
Okay. And it was quite difficult for the network with only one happy smiley to recognize distorted smileys. But once you train it with an extra happy smiley and an extra sad smiley, it will get easier for the network to differentiate between them. As you see, it only misses like two blocks now to be a happy smiley. So if you move a little bit down, please, you can see that this that our network, this is what I mean with the order matters a lot, because now we did happy, sad, sad, happy, I believe. And it just generates, you can still see that most of the sad smileys are sad, and most of the distorted sad smileys are distorted. But two as in 2 minutes. Okay, thanks. But I really wanted to show you that the order matters. So can you change the sad 0 to sad 0? Swap the last 2 around, please.
Oh, I see. Then that here, and then there's a comma.
Yes, that's it. Comma. Okay, this should work. And then run forward.
Fuck.
Don't. Okay, let's skip over the first bits.
You are on tape, you know. In any case, my dears, this is great. So here's a tada symbol for you, saying this is perfect. Would you like to conclude with one sentence?
Yes.
So that we are punctual.
Felix, conclude.
Okay. So the conclusion is we've made the Hopfield network. We made it correctly identify our happy and sad smileys through our training data. Like the type of training data you use matters. Like we haven't had time, but if we add 5 smileys as training data, it starts to have a lot of trouble actually trying to connect them. Like we can't show that, but it's interesting to play around. And then with the classification, adding the threshold, it also changes, like if there's a true or false, if it actually recognizes it. And that is all again linked to the confusion matrix. So in all the Hopfield networks, and here you can see last part, we trained it correctly, it recognized them all correctly, so you can see that in the Hopfield network. So this was our project set phase, eventually a success.
Sure.
It turned into happy face.
Excellent work. So this is really fun, and you have the full stack development. So this is brilliant. I want to actually share some more comments as we move forward, but I'm not going to do it now. We have 2 minutes for questions. Meanwhile, the matching law comes in. So we're going to have a couple of more Hopfields. And so questions for the presenters. Alex and Yona, you're welcome to join now and share your screen.
I had a question about the green dots
Oh.
in the pictures.
Yeah.
Like
So
I see sometimes the pictures change, but then the green dot is not there, and then sometimes it's there, but I don't really understand what it's
yeah.
actually doing.
I can explain that. So the green dot basically, the green dot means that the network is not sure if it should be a 0 or a 1 or a -1, because the bars are -1s and the yellows are 1. So the green is actually a 0. And then and if it disappears, the network decided, okay, this is a 1 or this is a 0. For example, here you can see this is a green one, and then it turns it into a 1. But sometimes it just can't figure it out and it stays a 0. And we see that because we've coded it with only 1s and -1s because Hopfield.
Because Hopfield. Yeah, there's a lot of statements to unpack here, but I think that this is really cool. Share this. I mean, I'm going to make a canvas for everybody to share their collabs, and then you guys can play and use each other's. Now we are anxiously anticipating the share from Alex and Jonah. Excellent. So there we go.
Can you see my screen?
Yes, we can. Thank you, Felix. Thank you, Julian. Great job.
Okay, so again, good morning, everyone. So let me start. So in this course, at least in the past few weeks, we have learned how reinforcement learning can help us train networks to take actions in an environment in such a way to maximize the total reward. So for example, we've seen how in reward learning, a network can encode values of rewards among different choices, such that what brings the highest reward ends up in the end being performed the most. So what we will discuss today is the matching law, which is closely related to the concept of reinforcement learning. And we will show how a perceptron, so a simple artificial neural network, is able to generate responses that are consistent with the phenomenon of probability matching, which is related to the matching law, and basically exploits and explores when confronting with a multi-armed bandit. So I'll introduce a few concepts. So operant conditioning is which is also called instrumental conditioning, is a type of associative learning process through which the strength of a behavior is basically modified either by reinforcement or punishment, which basically underlies the reinforcement learning. And in operant conditioning, the matching law states that in concurrent schedules of reinforcement, there is a proportional relationship between the relative response rate and the relative reinforcement rates. And what does that mean? So this law was formulated by Herrnstein after an experiment in which pigeons were put into a box and presented with two buttons. And each one of the two buttons led to rates of food reward that were different. And what the experiment showed is that pigeons tended to pick the button that yielded the graded food reward more than the other button. And the radio of choice of the two buttons matched the radio of the rates of reward. So as you can see from the formula, which is shown here, B's, which are the response rates, the radio of the two is equal to the ratio of the R's, which are instead the reinforcement rates. And well, nowadays this matching law is used often by economists and behaviorists to either try to describe or to predict patterns of behavior. This phenomenon, which occurred in the experiment, is often referred to as the probability matching phenomenon, in which basically a subject that is facing a sequence of choices matches the probability of the choices with the probability of reward. So what we tried to do is basically reproduce a research by Donson, and we tested whether a perceptron was able to exhibit this matching behavior. So just to remind you, a perceptron is a single layered neural network which consists of input and output units. So it's going to have incoming input values, which are going to pass through some weights. We're going to get the weighted sum. And then ultimately there is going to be an activation function, which ultimately leads to the output. But I'll leave the details for later. And what we tried to do is first, we tested whether a perceptron was able to mimic the matching behavior. And we trained it to change the connection weights in accordance with the reinforcement probabilities. And then in the second part instead, always using a perceptron, we tried to simulate the multi-arm bandit problem. And this is a problem of choice behavior in which basically an agent must allocate a fixed limited set of resources between competing choices in a way that maximizes their expected gain. But each choice's reward is unknown at the start. So an example is if a player went to the casino and was faced with, for example, 4 slots machines, and he could pull one lever, so one machine at the time, and he would learn basically by pulling the levers what the probabilities of reward were for each machine. But yeah, I'll let Jonna explain the details of the model.
Yeah, so the model we chose to create incorporated 4 different discriminative stimuli, each with their own respective reinforcement rates. And then after 300 cycles, these reinforcement rates were flipped to test the adaptability of the stimuli. The activation function that we incorporated into the perceptrons was a sigmoid function visible on the right, which you are probably all quite familiar with by now. However, other activation functions can also be used to achieve a similar result. As was previously mentioned, in the first simulation, the pure probability matching potential of the perceptrons was tested. And thereafter, in the second simulation, a greed function was incorporated to allow simulation of the multi-ordered bandit problem, where the perceptron tries to export the higher probability stimuli and as a result, test those more frequently. Here, the actual setup of the model is visible. It should be noted that one of the assumptions of this model is that only one discriminative stimuli can be activated or tested at once, and thus all stimuli would then either be a 1 or a 0. The perceptron then took this input and using its respective weight determined the net input function, which it then used as an input into its activation function, the sigmoid function. This then determined the output of that cycle of the perceptron, which was then compared to the actual machine output at the time. The difference, or lack thereof, between those 2 values was then used to update the weights. The rates at which this weight was updated was dependent on the learning rate, eta, which is visible in the formula box below the update weights, where R represents the realized output of the machine and E represents the expected output of the machine. Now, what is the machine input and output, you may be wondering? This is simply the probability of reinforcement or the probability of receiving a reward, 1 in this case, for the activation of one desired stimuli. The probability of each of these stimuli producing a reward was equally distributed, similarly to in our paper, with a 20% increase per stimuli. DS1 thus has a 20% chance of producing a reward if activated, DS2 40%, DS3 60%, and DS4 80%. Thus, depending on which input was activated, the machine function determined whether or not this input actually gave you a reward. Simulation 2, on the other hand, is very similar to simulation 1, using the same input weights and activation function constructions. However, in order to incorporate the greed function and thus the exploration associated with the multi-arm bandit problem, an additional step was introduced between the perceptron output and updating the weights. This was done by having the greed function decide to only update the weights depending on how much the perceptron perceives the weight as. So to put this into better context, if we take a 0.7% weight for the first discriminative stimuli, this would mean that there would be a 70% chance of the weight being updated for each cycle of perceptron experiences, meaning that the weights are updated relatively more frequently for the higher perceived probabilities than for the lower perceived probabilities. And that's in order to simulate greed. This would be analogous to having the mouse pull its perceived higher probability lever more often, allowing it to learn quicker about this lever. When analyzing the results of our simulations, which are visible on the left, and comparing them to the paper simulations, which are visible on the right, we see that we are able to effectively and accurately recreate the results. This in turn means that the perceptrons accurately adjust their weights until they're at the machine probabilities, indicating that perceptrons and neural networks are indeed capable of recreating the matching model. It should be noted that after 300 cycles, the machine probabilities, as I mentioned earlier, were switched in order to test the adaptability of the system. And as is visible, it was accurately able to adapt to these new probabilities. It should also be mentioned that in simulation 1, all of the input stimuli were tested equally, which was not the case in simulation 2, of course, as a result of that green function I previously mentioned. There are additionally some other differences that can be noticed. One of the most notable being that our simulations were more precise and had a higher level of detail than in the paper. And this stems from the fact that our paper makes averages based, their paper makes averages based on every 10 cycles in both the training and update stage. Additionally, there were also clear differences that can be seen when comparing simulations 1 and 2, namely how simulation 2 as a whole takes a much longer amount of time to update and reach the desired target weights. This slower adaptation in simulation 2 is much more evident when you compare the discrete simuluses 1 and 4, especially when the actual switch occurs. 4 drops off much more rapidly compared to the increase of 1. And that would be more evident, for example, if you were to draw a tangent on the slopes at the initial stages of the switch. Now, why this occurs can best be explained by introducing a new simulation where the machine probabilities were changed 5 times over the course of the simulation. These probabilities are visible in this diagram as the dotted lines, which change by the same amount, like for example, minus 0.1 or plus 0.15 for both the higher and lower probabilities. However, the starting points are different, being 0.25 and 0.75 respectively. It's clearly visible in simulation 1 that the adaptation when randomly and equally choosing which input weight is tested is the same rate for both higher and lower probabilities. However, for simulation 2, this adaptation occurs at a much slower rate for the lower perceived probabilities and much quicker for the higher perceived probabilities, sometimes by up to as much as a factor 3, which is seen in the middle region of that simulation. This demonstrates that our model is accurately able to reproduce greed, as the higher probabilities should be updating at a much quicker rate, which occurred, and that simulates that these are used more often. The influence of the learning rate can additionally be analyzed in our results. Another basic simulation was introduced to determine the effect of this learning rate, in which the perceptron has to start at expecting a 50% reward probability and increase to match that 80% reward probability. From this, we can gather various conclusions on the impact of the learning rate on this model as a whole, and how this can be optimized. For example, when analyzing incredibly small learning rates, which is visible on the left and takes a value of eta to be around 0.0005, you can notice a much longer learning time, which is exaggerated even more in simulation 2. You also notice how there's relatively little noise in the learning curve. This is especially not the case when analyzing the larger learning rates, such as when eta is 0.05, which is visible on the right. Here, the learning time is much shorter, barely taking 150 cycles to reach the desired target. However, as a result of the larger learning rate, lots of noise was created in the simulation, where it bounces up and down around the desired 0.8 target by up to as much as 0.1%, an almost 15% deviation from the desired target. It was for this reason a compromise between slow learning times and noise had to be found, and this compromise was found to be around 0.001, visible in the middle diagram. And it should also be noted that this was additionally the learning rate they found to be optimal in the paper, suggesting the accuracy of the finding.
Hi, John. I don't know if you saw my indications, but can you wrap up?
Yeah, there's like 2 more slides. So
yeah, just skip them.
Oh, yeah. So yeah, basically, there's sigmoid function isn't the only activation function that can be implemented for the perceptron. You can also use the pursuit algorithm, about confidence bound, gradient descent, and softmax. And these are all able to accurately reach the results that we found. The adaptability of the model does, however, come with some limitations. One of these is namely that it could be argued that the perceptron itself is not capable of true operant learning, because the greed function is merely taking a probability of it updating in place of it's selecting the desired stimuli, so it's sort of externally controlled. And various variables are not also able to be introduced into the model, such as like bias or producing over and under matching. And this occurs.
Allow me to interrupt you. Thank you. I think that it was an absolutely super clear presentation. Here's a ta-da for you. We have to move forward I wanted to open for questions before we get late. Do you mind me interrupting you? I'm sure you do. I apologize. This has been great. Thank you for showing these slides all the way to the end. Questions from the crowd? No questions whatsoever. This was excellent. Like, it was not only reproducing the paper, but also original and forward thinking. So I really appreciate it. We do have to move on, however, with the next presentation to make sure that we're going to be finishing on time. So now we're going to go to another Hopfield version. And so Marian and Mays, would you please kindly join in and let's take the opportunity also. You can go vote and ask questions to Jonah and Alessandro, because this was in the chat, if you like, and this was absolutely, on the mark, on the money. Thank you kindly.
Are we good to go? Yes. All right. So in our project, we tried to train the modern Hopfield network to recognize the patterns within a particular context. And our project and our work is novel because we use the new architecture to combine two separate modern Hopfield networks, which on their behalf produce two different outputs. And these two different independent outputs are combined in the final layer of neurons. So in order to give you a better impression what our model is able to do, I want to start with a small example. Yes. Could you please either say out loud or type in the chat which letter you see on the screen?
R.
R. Yes. Any other versions? R. Great.
I thought it was a ya in Russian.
Also could be. Yes. Yeah. But now what letter do you see? Oh, I cannot move on. Yeah. What letter do you see here?
An L.
How would you read out the word?
Apple.
Apple. It's quite clear.
Apple.
Yes. So in the next slide now, I will explain what just happened, and I will guide you through the cognitive background. From there, we will move from the original network to the modern Hopfield network, and then we will go into details of architecture of our model and wrap up with another example. Okay, great. So what did just happen? Even though you were exposed to two identical stimuli in the second and the third slides, your interpretation of the stimulus changed as you were provided with the context. Therefore, we can conclude that the context biases the perceiver towards the certain patterns. The perception of the situation depends on the complex interplay of bottom-up and top-down processes. And in many cases, such as this one, the evidence is equivocal and it's open to multiple interpretations. And top-down stored information might automatically fill the gap and thus create a bias, which will crucially affect the appraisal of the situation. We know that the learned sequences are used to recognize and disambiguate the incoming information. And with the context, we create the expectation of what the next stimulus is going to be. And in this case, when we say the context, we mean the first four letters of the word apple. And it has been suggested that all these above mentioned functions are provided by the neocortex, which is the most recently developed part of the cortex. And it has been also suggested that it permanently constructs the spatial and temporal, but in this case, we focus on the spatial models of the sequences it is constantly exposed to, and its primary function would be to predict the future, to predict the future stimuli. Yeah. From now on, we'll explain briefly what the Hopfield network is. Mace?
Okay, yeah, so we already had an entire presentation on the Hopfield network. The most important thing I want you to remember is that in a Hopfield network, we store memories as attractors in a dynamical system. So in a Hopfield network, every neuron is associated with an energy level. You can see this energy level as how badly this neuron wants to flip. So like flipping being going from 0 to 1 or 1 to 0, on or off to on. And the energy level of an entire network is the energy level of all these neurons combined together. So if you see the network as a ball in this energy landscape, you can think of updating it or like going to the next time step as falling down into one of those attractors. And if you like add a little bit of noise to the to a picture, in this case, it will converge into one of those attractors. But next slide, if you, next one, you see that if you add too much noise to the Hopfield network, it doesn't exactly recognize, it doesn't converge to one of the stored memories before. But like the memories were the attractors, right? So what's happening here? Well, the memories aren't the only attractors in a Hopfield network, but there are also attractors called spurious states. These spurious states are a combination of the other memories you store and become a problem when they take up a large portion of the phase state, meaning a large portion of possible states won't converge into one of your memories anymore. The even bigger problem of the original Hopfield network, which is also what Felix already told you, is that it has a very low storage capacity. So if you try to store too many memories, you will have multiple memories converging or like becoming one bigger memory or attractor. So if you go back to the previous slide for one bit, I want you to think about like moving these valleys, these memories closer and closer together. At one point, they will collapse into one bigger valley. And this is called bifurcation. And now the individual memories are not stable anymore. So modern Hopfield network, also known as dense associative memories, addresses both of these problems through changing the update rule. And with this update rule, we basically go from a linear function in the energy to a power function, which makes the valleys way steeper. And as a result, we can store way more memories in the Hopfield network.
Great. Yeah. Now, as we mentioned at the beginning, our model consists of two separate Hopfield networks. Now we'll go through what each of them does. As for the first modern Hopfield network is indicated by the arrow. What we did in that one, we stored a particular list of words such as Apple, Joker, Japan, etc. And as you can see on the screen, if we input the incomplete part of one of the words, such as Japan without N, it will predict that the next letter is going to be N. And because Japan is the only word on the list that starts with the similar pattern, it will predict almost with 100% certainty that the next letter is going to be N. However, for instance, if we input the APPL, which is shared by the two words, Apple and apply, it will say that the probability that the next letter is either E or Y is approximately 0.5 for each of them.
So how do we store memories in this network? In this case, for every location in the word and character, we have one neuron. So in our case, the A neuron in the first location of the word is lit up. And what happens if we now try to input Apple without the E? You will see that the energy in all of those neurons is almost close to zero, but in the E, it's very high because it really wants to flip.
Mm-hmm.
And this energy is where we derive the probabilities from you see in the slides.
Right. Now, that being said, as for the second independent network, what it does, it tries to recognize, tries to extract the information from the patterns that it is exposed to. Basically, this second Hopfield network does what you guys did when we showed you this particular letter, and that you said it was going to be R. Because it is not, the boundaries are not always very clear, it has several versions, and it compares this patterns that it extracts to every every letter from the 26-letter alphabet, and it produces the certainty rates for every one of them, and finally outputs the highest certainty. So in this case, the highest certainty rate would be for the letter R, as also in your case.
Okay, so memories in this network are a little bit more interesting. So you can see we store an image and we store an association score with this image. So what this means is if we get input, we go through every memory and we compare it with the memory. And if it's close to that memory, we subtract or we add a little bit of probability to the classification of this image. So for example, for this memory, if the input is similar to this memory, for the A, it will add a little bit of probability being classified to that, because the A has like a score of 1. And for the H, it will go down in probability. So what we do is we have a bunch of these memories, and you can see that's in the next slide. And we go over all these memories individually, and then we add all these probabilities together to, in the end, get all these classifications scores. And yeah, that's the process.
Now, what happens in the final layer whereby the two independent outputs are combined? As we saw in the Apple example, just to revise quickly, the first network said that the next letter was going to be E, it would predict the word Apple, and then the second network recognized this letter as R. However, what happens now in the final set of neurons is that the final prediction, the prediction by the Hopfield network number 1 and Hopfield network number 2 are combined with their respective weights with which they project to this final set of neurons. And then this probabilities, these values get summarized, and this gives us the value for the final prediction. And then the node in the final set of neurons, which each of them signifies each letters from the alphabet, the node which receives the highest of these final predictions is lit up. So in this case, whereby the input was Apple and the initial prediction was E. However, as you saw in the previous slide, the letter prediction was R. The network was still able to give us the E as the final prediction. So this cognitively we can translate into the fact that interpretation of ambiguous stimuli is not a purely data-driven process, even though we can see something as R when we're provided with a context, we see it in its respective shape, and it can exemplify that our top-down stored sequences bias towards certain interpretation, and the perception of the situation depends on the complex interplay of bottom-up and top-down processes. So in this final slide, it happens. It's simulated what you guys did in the previous slide, when some of you saw it as an E, but some of you saw it as an R, and when after you saw the word Apple, you were able to read it out as the word Apple. So this is exactly what happened in the final convergence layer of neurons. However, sometimes it happens when the evidence, such as W in this case, is not open to the interpretation, and the boundaries and the contours of the image are quite clear. So for instance, in this case, I assume you can quite clearly see that it doesn't say Apple, it's Apple, and the final letter is definitely the W. So what does our network do in this case when even though the context creates the bias, the letter, the bottom-up information is clearly not what it is supposed to be according to the stored sequence. So when this happens, when we provide the second layer with this image and the first layer with still the Apple input, our network is still able to clearly predict that this is indeed the letter W. So what does it simulate in our brains?
Sorry, Mariam. One more sentence.
One more sentence. So without this function, we would not be able to recognize errors and the differences in our surrounding environment. And this is the conclusion. We created a novel architecture which simulates the character recognition based on context.
Okay, very good. Congratulations. So questions? You have time for one question, and then the next group can already join in.
Not a question, but I think it's very cool that you used the profile pictures. It was very sick, man.
Thank you.
Yeah, I also think that you made a very good job in delivering like so much information in so little time. Impressive stuff. So who is next? Please vote to group 3. And let's move on to group 4. Thank you, Carlo. Thank you, Fong.
Yeah, okay. So evaluating the effectiveness of a network is a key process when it comes to classifying. We want eventually our model to be able to classify well and overall perform well. So our presentation today will look at how we can evaluate, quantify the performance of a network using confusion matrices. But first off, we will look at how binary classifiers work. How do we classify stuff? So classifiers are artificial neurons that decide whether an input belongs to a certain label or not. So this is a very explanatory example. So you give it an input, it asks a question, is it a cow? And it answers yes or no. This is also another more complex example, looking at the perceptron. So it classifies in the way that it takes the sum of the weighted inputs, it passes through an activation function which has a certain threshold. If the sum is over the threshold, then the neuron will fire. And if it's lower than the threshold, then the neuron will not fire. So as part of this presentation, we've decided to give Project 5 DIY receptive field a little shaping. So as a little reminder, at the end of the project, we'll build a feedforward neural network of classifiers that was classifying orientations of bars. So we had 4 different labels, vertical, horizontal, diagonal left, and diagonal right. So we've decided to add some distorted stimuli in order to test our network. So here you can see our distorted stimuli. We've kept the orientations of bars, but we've added a 1 pixel. And we've also lowered our threshold to 2 instead of 3. So now our network is recognizing pairs of stimuli, 2 pairs of stimuli, sorry, instead of 3. So it enables to not classify it well. So as an example, to make it more clear, our first distorted stimuli is supposed to be a vertical line, but because it only recognizes 2 pairs, it also recognizes it as a diagonal right. Okay. So here you can't actually count the mistakes by hand, but what if we had a bigger network? What if we were able to use machine learning? Then we need some type of tool to quantify the performance. And this is when confusion matrices come into place. So basically, confusion matrices are a summarized table of the correct and incorrect predictions that a network does. It also enables you to directly visualize whether stimuli was classified well. Here you can see the fundamental building blocks of a confusion matrix. So these 4 outputs, true positive, false positive, and true negative. So to explain them, we have a little example. So here we have a network that classifies emails as spam or non-spam. So a true positive would mean that a spam was classified as a spam. A false negative would mean that a spam was classified wrongly, so as a non-spam, and the rest is pretty self-explanatory. So with these, you can further quantify the performance using some metrics like sensitivity, specificity, precision, negative predictive value. And you also have accuracy, which is used a lot in machine learning, for example, and which describes how regularly the model predicts the correct outputs. so the proportion of the number of predictions that are actually correct. So as I said earlier, we redid the project 5 Java receptive field in order to build our own confusion matrix. So as you can see, it's a little bit more complex than what we've just seen because it has multiple classes. So as I said earlier, we have 4 different classes. On the x-axis, you can see the predicted labels, and on the y-axis, you can see the true labels. So what we are aiming here visually is to have all of our data in the diagonal, which represent as well the true positives. So this is how you would analyze a confusion matrix. And if you want to look class by class, you can perceive the confusion matrix in that way. So as for example, if we're looking at diagonal left as a true label, diagonal left predicted, it would be the true positive. The false negative would be the ones on the side. And yeah, that's how you would look at a confusion matrix class by class.
Okay, so you can look at the confusion matrix and maybe look at accuracy, but if with a complex model, you can also use a loss function to more efficiently evaluate your model. So a loss function, also known as a cost function or sometimes an error function. And in simple terms, it's just a value that you can use to estimate, evaluate, rank, or compare your model or models. Next slide, please. Okay, so one type of loss function that we're going to use here to evaluate our model is the cross-entropy category loss. And it's just, so the category loss is just a variation of the cross-entropy. And basically the cross-entropy compare the predicted probability distribution and the target probability distribution. So in simple terms, you want to compare your models, the values that you have of your models with the target models that you want to achieve. And here's the formula. The y hat is the predicted probability and the y is the target probability. There will be an example later, so you don't have to focus on figuring out the formula. So the cross-entropy category loss used this specific function called the softmax function, and it converts real values into probabilities between 0 and 1. And the output of each class depends on the output of other classes, and all of the components add up to 1. So here's a formula as well. And now we're going to go into an example so that you can better understand it. So again, going back to our confusion matrix, we have a predictive label as our x-axis and the true label as our y-axis. And let's focus on the top row where the true label is the vertical and you have different values for the predicted values. So only looking at this row, you may be able to say, well, the model that we have right now is not perfect, but to what extent and what you can improve, you cannot comment on that. So we can use the softmax function and the cross-entropy category loss. But first, because the true label we have here is vertical, we know that the target probability should have been 1, and the predicted probability should have been 0 for other orientations. Next slide, please. So for the formula, this is the softmax function. We use this to turn real values.
My mistake, not 2 minutes. So you have another 5, sorry. Yeah.
Okay, so you can use this function to turn real values into probabilities. And here in the numerator, you have the exponential of each value we have here. So for vertical, you have exponential of 2, horizontal exponential of 0, and that goes on. And if you sum all of these values up, you will have the denominator of the softmax function. Okay, so here's a better visualization of the function. You take the numerator, which is an explanation, of the values divided by the sum of all the explanation of the values. And then you have the y hat, the predicted probability, which is the probabilities that you got the correct label. So for example, vertical is 63%. You got the label of vertical 63% of the time, horizontal 9% of the time, and that goes on. So after turning our values into probabilities, we can have here the y hat, which is the predicted probability as the previous line, and the y, which is the target probability. Like I said before, vertical as 1 and other orientation is 0. And we apply the cross entropy function to have the outcome of around 0.2. And so to summarize, with confusion matrix, you can apply the softmax function to get the probabilities, and then use the cross entropy loss function to get the loss values. And here the loss value is 0.2, which means that our model isn't doing too bad. But if you want to improve the model, you can try to decreasing this value so that it approach 0 by increasing the probability of vertical, which is the true label and the correct label, and decreasing the probability of incorrect labels. So from the beginning, we have talking about the confusion matrix, and we have relating it to the loss function and the cross entropy category loss function. There are also a lot more method you can use to evaluate your models, but we hope that we can introduce you a little bit about these topics. And this is also the end of our presentation. Thank you for your time and patience. If you have questions, please.
That was very informative. I hope that you all learned. So I have a short one. So you take the softmax function and you basically create a denominator that normalizes the numerator. What would have happened if instead of using the softmax, you just use the values of the confusion matrix directly, like to create the loss function? I mean, why do we use exponentials and logarithms? Do you know?
I don't think I know, because I'm not very good at math, but because we're using
You've
this
done
specific,
a good job though, then.
because we're using this specific cross entropy category loss function, which is used for multi-class classification, which is our models. So loss function, there's a lot of method that you can use depending on how you design your model. But the details I really can't explain.
Anyone has an idea? Out of curiosity, basically close to the break, so maybe you have thought about it a bit. So the softmax function pushes augments the difference between the highly active ones and the not so active ones. So if you don't use the exponential, then there are two reasons really. One is that, I mean, you're basically maximizing the distance between the highly activated one and the not so activated ones. We convert that into it's very much of a, that's why soft max, I mean, it's a maximum function. It's trying to find out which one is the maximum value, but it's soft because it doesn't make all of the other ones 0 and 1. Thank you, Julian. Cannot vote yet. I'm going to do that now. Okay. Yeah, and the second reason is that the logarithm and the cross entropy loss relates directly to the theory of information theory and the content of information in these different outputs. Just wanted to mention these two things. Explaining them would take more than 1.5 minutes. So this was the first block of presentations. Absolutely gorgeous work, everyone. So I would suggest we now have a 5-minute pause and we make it sharp, or 6-minute pause, and the presenters can come in 5 minutes and already start sharing. And we will have the opportunity of discussing this more in the future but today we're just gonna save our contributions with these steps. I am looking forward to the next block of presentations. Shall we move forward? Okay, take your time. I'll see you shortly.
Can I ask a question during the break?
Yeah.
After the exam, there are going to be open questions, right?
Yeah.
Or no? Okay.
Yeah, but they all look very much like the ones in Brainscape. So like if I ask you, okay, well, what's the difference between AMPA and
An MDA.
yeah, AMPA and GABA, for example, or
Just
GABA.
make sure. Just
Yeah. So there are some, but yeah, they look like the questions in Brainscape, only that you wouldn't be given some multiple choices to select the correct one.
good to know. Thank you.
Or at least, so I hope you will be the judge afterwards.
Thanks.
I saw that you've done all of the Brainscape cards, so you're tended for, I'm sure.
Thank you.
All right, so Genzo, share the screenshot.
Yeah, so initially we prepared like a handout during the presentation so that everyone could follow the process.
Ah, that's cool.
But we couldn't, so we just thought that we can take a screenshot of it and just put it in the chat so that like people can follow.
Smart. So yeah. Excellent. So I did answer your mail eventually in the morning. I'm sorry. It's
so
really
much.
tough. Okay. But I appreciate it. So I think that this handout is going to be, I hope that people will save it forever.
Yeah, I mean, I think the presentation will be maybe more helpful, but yeah, I think it's better to just like keep looking from there because it gets confusing even for us like while we tell. So I think it's
understandably. Did the links that I sent you, did they help clarify what the minimal setup looked like?
Yeah, I think you already like explained kind of that before you've sent this, so it made more sense to me because you already explained to me before.
Yeah,
so.
I mean, it's really the breaking into pieces that is the art, and I do think that doing it all in 1 week is very tough. But my perception of your work is that you've done the impossible. I mean, like you basically, yeah, I mean, you've understood the entire set, or like with maybe small translation, might be some specific, if you had to rebuild it from scratch, you might have to check a couple of details, but in general, if you're using it, you understand like the entire system. So I'm really happy about that.
At least for
is
my
it already? Yes. It's 10:05, right? Like I am getting confused with my own schedule. So we said that it's going to be 10:05, right? You started. Yes, 10:05. Yeah, so we can even have a little bit more of a conversation if you'd like.
I was just wondering, like, since we are not able to tell everything, like we're gonna upload the slides to somewhere as well, right? Like,
yeah, I've created a forum thread in the discussion so that everybody can upload whatever they've done. So the Google Colabs, the slides, maybe create some links. I mean, I think. Since now we've been introduced to all of this, then now we have the time to at leisure see what has been done, and learn more.
Yeah.
I think I didn't want to judge these contributions as full-fledged reports, because I would prefer that people focus on preparing the presentations and working on the projects than really taking the time to even write a report is overkill, I think. But yeah, I'm hoping that the material, the content itself is also going to be judged during the presentation. I think as people are going through, they're already, basically judging the content and so forth. And so all the links in the discussions, then people can at leisure go and find out more about what the projects actually look like.
Yeah, I mean, it's a shame that I can't like explain what I know in my head, like all of those details, but I'll try to like make it more simple and just like choose some stuff to tell because we don't have much time.
Yeah, I mean,
It was really helpful to talk with you.
yeah. Again, I mean, like it's another one of this multidimensional arts. No, I mean, like the art of teaching is not telling people everything you know, but selecting the things that make what you know most available to them later.
Yeah.
And creating a step ladder. And so it's really tough. Like my tendency, as with you, as with people like Mariam, I mean, like is being overly explicit. I mean, and so saying everything, and so that's I fight back.
Thank you so much. Should we start sharing the screen already?
Yeah, I think it's a good idea. So then we can start exactly timely, or even 1 minute before, if most people are back. Let's actually get some thumbs up from everybody that is back, and we're going to be starting in 1 minute.
So
yeah,
I'm not sure if I should open the present mode, because then it doesn't allow me to show GIFs. So is it okay if I just present in this like format?
As you prefer, your choice. I think you can start whenever you like, Chenzo and Lisa. One of the reasons being, you know, this is being recorded, as you know.
Okay, I thought like everybody is not here anymore, like yet. So.
Not everybody is here, but as we should have been returning 10:05 punctually, you know, the first 2 or 3 statements they might lose, and they have to go back to the video.
Okay, so good morning, everyone. Today we'll be presenting our final project, which is about basal ganglia and how does it have a role in action selection. So we'll first start with the biological processes, and then move on to how theoretical model explains this process is going on in basal ganglia, and then show you what is it, how is it implemented in Nengo, and how do we run simulations to show how they're related to each other.
Okay, so the basal ganglia is a group of subcortical structures, and like the main thing that the basal ganglia does is action selection via initiating action and suppressing some other actions with direct, indirect, and hyperdirect pathway.
Yeah, so this is the model, and I already sent a screenshot so that you can follow during the process that we're going to tell. And it's basically the model by Stewart and his colleagues and Elias Smith. And what it basically shows that how information runs through the basal ganglia, and how through the mutual inhibition, basal ganglia chooses one action only through a lot of possible options. So we'll go through this step by step by starting first with the direct pathway.
Okay, so we have the direct pathway, and the function of the direct pathway is to select actions, to initiate action. It chooses the most relevant action, and you can see it in the image here beneath, that what the direct pathway does.
Yeah, so it's basically we will start from the cortex, go into the striatum D1 and the GPI for the direct pathway.
So we'll start in the cortex, and all the information from the cortex is being sent to the striatum D1. The striatum consists of the striatum D1 and the striatum D2, but the striatum D1 is the part for the direct pathway, and it consists of dopamine D1 receptors.
And it gets an exciter connection from the cortex to the striatum D1.
Yeah, and the striatum D1 then sends inhibitory connections to the GPI, and the GPI is actually a thing that inhibits action. So when it, when we go from it gets inhibitory action to the GPI, and when the GPI gets inhibitory connection, it actually initiates action, because that's the thing when you have a thing that initiates action, it's being inhibited. You know, it inhibits action. When it's being inhibited, it initiates action.
Yeah. So just because GPI has an inhibitory connection to thalamus, the most inhibited action in GPI is going to be the one that is selected at the end.
So then we have the indirect pathway, and the indirect pathway is the control pathway, and it is for suppressing actions. So in our brain, we have like 1 million actions we can like do per minute even, but we only can do one action at one time. So the indirect pathway is to suppress the other actions.
Yeah, at the end, it's going to inhibit the other possible actions in order to choose one of them. So it's like a control system that modulates this process.
It starts again in the cortex, and now from the cortex, it goes to the striatum D2. That's the other part of the striatum, and it sends excitatory. It's an excitatory connection.
Yeah, and we're now here, and then we'll move on to its inhibitory connection to GPI. Yeah, and here we have inhibitory connections via the GABA neurotransmitter coming to the GPI from this time D2.
Okay, then we go from the GPE. That's the thing that only the indirect pathway has, from the GPE to the STN. And this is an inhibitory connection as well. And from the STN, it goes via an excitatory connection to the GPI. And this is the part where it goes back to the direct pathway, and where the direct and indirect pathway like talk to each other there.
Yeah, it's kind of like competition happening in order to choose one action at the end. So here we, in the GPI part, we have an inhibitory connection going both to subthalamic nucleus and to the GPI. So this is the part happening from, so GPI has 2 inhibitory connections to these parts.
Yeah, so it goes from the STN to GPI, what I just told. Here is the part where I just told you that the GPI inhibits action. So when you get an excitatory connection to a thing that inhibits action, it actually inhibits the action.
Yeah. And then we are GPI receives these inputs from like the direct pathway, the indirect pathway, and the excitatory connection from STN. And at the end, it's going to choose which type of action has to be selected, and that is going to send to the thalamus for it to do that.
Okay, and then we have an extra pathway, because I just told you that the GPI gets connection from the striatum D1 via the direct pathway, and from the STN via the indirect pathway. You can see it in the image we sent you. But if it gets inhibitory connection from the direct pathway from the striatum D1 and it gets excitatory connection from the STN, it doesn't know what to do. It's indecisive. So that's where the hyperdirect pathway steps in, and it gets extra excitatory information.
Yeah, so basically we have the input from cortex going to the STN directly, so that it allows the GPI to select only the most inhibited action in the GPI, and otherwise we would select more than one action if this doesn't include in the indirect pathway.
And then we have action selection, and the thing that we've been talking about, like this whole thing is that choosing an action out of the possible actions that are available. This is via mutual inhibition. So it only chooses one thing and the rest is being inhibited. And that is via the input with the highest utility. You can see it in the right picture in front of you. Here on the left side, we see the utilities, the 0.3 and that kind of stuff, and via the direct pathway and hyperdirect pathway. Here you see that one action is being selected, and that's the 0. Mm-hmm. And the one with the lowest value is being selected because of the inhibitory connection
to thalamus. So basically, if just because GPI has an inhibitory function, it's for us to choose an action, we have to give the lowest value possible to inhibit the thalamus less, so that thalamus knows, oh, okay, I have to select this one. So that is what's happening. And actually, you can also see it from this picture where we have this input and the output spikes, and the most higher the utility, the more it's inhibited in here. And then we move on to how this is implemented in Nengo. So basically, Nengo is a tool for creating and simulating brain models like these. And we use the model by Stuart Eli Smith from 2010. And so this is how we use Nengo. We enter some sort of input, and then we see how it's shows the output. So we enter a value for specific, emphasizing specific action, and then we will see what the action is here done in here. Sorry, just, yeah. So I just want to tell you a bit more about the assumptions. So here we have a spiking model where they use lift neurons instead of like rate neurons, which was used in Gurney's model that they based in, and they wanted to use that for best approximation. And in each component, we have some group of neurons, like a population of neurons encoding these information. And in the Nengo, we have this vision component where it is represented as the cortex, and we have 32 dimensions here to encode concepts that are possible. So in our task, we'll see which concepts are being encoded, but basically this is the part where the perceived concepts are encoded via 32 dimensions. And then this is going to be mapped to a 5-dimensional vector, which goes into the basal ganglia as the input. And then basal ganglia is going to calculate which action that it should choose, depending on the dot product that we'll show you later. So this model is basically built on a SPA architecture. And what it means is that each concept that the system knows is encoded via some vectors called semantic pointers. So these semantic pointers are high dimensional vectors that encode the concepts. So they act as like the concepts that are close to each other are represented by the semantic space. And the basal ganglia, apparently what they assumed in the model is that it looks at the similarity between the semantic pointer and the input that it receives. And now we see here that we have 4 types of action. So we have the first action dog, which is if the, so the basal ganglia, what it does is that in the input, we have every possible concepts that are perceived at that moment coming into the basal ganglia. And basal ganglia looks at the input vector and it says, okay, I know the semantic pointers for each action that I already know in the system, and it compares, it gets the correlation via the dot product and chooses that, okay, how the input vector is similar to the weights that I've encoded, looking at the semantic pointer. And then according to that, it chooses one action with the highest utility value and gives the consequence. So for the dog, it's gonna bark, for the cat, it's gonna meow, and so on. So we have 4 actions represented in the Nengo with this code. And so this is the representation in the basal ganglia. And we have 5 neuron groups in each component encoding the input vector, and each receives a dimension from the 5-dimensional vector input vector. And each group has 100 neurons in it. And what it will see later on is that when we deliberately increase a value of a certain concept in the input vector. So we have a lot of concepts perceived in the input vector, but what we did in the simulation is that for each concept, we looked at what if we increase this value a bit more in the inputs. And for example, we entered cat's value, and then it's will have the highest value and it will choose the highest one and mutually inhibit the rest. As we will see here, for example, in ST1, we have more activation in the group 1, which we thought that when we run the program, the weights are trained such that certain group of neurons highly activate more to a certain concept, so that they're probably get it in group 1 for the cat. And for example, when we entered rat, we made rat a bit higher in the value compared to the rest. We're gonna see the group 2 activate more because they're trained in that way. And then at the output, for example, in the cat, we see the basal ganglia giving an output 0 for the chosen action, which is the cat, represented by the green line. And then we will see in the output that it's gonna show the meow in the speech. So now we're gonna show you the type of simulations that we did in order to show this. So in the condition 1, we just put dog input and we observed, okay, what happens in each group of neurons, like what type of activity do we see there? And when we look at ST1, ST2, and STN, we have similar type of patterns going on, and that the group of neurons that highly activated for dog, that are trained to be activated more for the dog, shows more spiking activity, and it mutually inhibits the other activities from happening from spiking. So we see, and this input goes to both GPE via the indirect pathway and GPI via the direct pathway. And in the GPE, just because we have an inhibitory connection, we have to see that the action that is going to be selected is going to be the inhibited the most in GPE and GPI, which we see here because we entered dog, which was highly activated in ST1, ST2, the input when they receive the input. And now we see that it's inhibited the most because there's less frequent activity, less neurons are activated compared to the rest. Because here you can see the number of neurons, which we have 100 in each group, and how much of the neurons are activated. And when we look at the GPI output at the end, we see all of the connections coming into GPI is going to be the group 0 that is inhibited the most because it is the one that reacts more to the dog. And in the output, we see how it's chosen, giving the value of 0 from basal ganglia, goes to the thalamus and knows that it should choose the action 0, and it computes the action via the bark. And we run obviously different simulations. And
sorry, Chanzu. Please wrap it up. Can you come to the last slide?
Yeah, sure. So basically, then we put more competition going on by adding more dog and cat at the same time, but we deliberately reduced the value of cat a bit more. And at the end, we still saw that basal ganglia only chose dog because when it computed the utility values for each action, it realized that dog had more utility, more like desirability, more similarity between the input and the weight that it knows, so that it chose dog anyways, even though it had more competition in these conditions. And so basically what we can see here in the conclusion is that we show you how the basal ganglia model and the mutual inhibition process works in order to select one action from other possible actions. And this is via the direct, indirect, and hyperdirect pathways that are competing with each other in order to choose one action at that current time. And they, Elias Smith and colleagues use SPA architecture to do that. And they show that each concept is represented by a vector. And what basal ganglia does is that it looks at the input vector that has the concepts perceived and looks at the similarity and correlation between what it knows by the semantic pointer versus what it gets from the input, and looks at, okay, the input that I'm getting, how similar it is to what I know, the ways that I encoded for the concept. And we try to unpack every detail as much as we can by showing the simulations that we did in Mango and how we changed simulations to show how it's related to the action selection process.
Okay, you can close it now. Yeah. Thank you so much. I mean, like, this is amazing that you are able to explain the entire Mango basal ganglia in 15 minutes. But you did use all the 15 minutes, so we're not gonna have time for questions. Can you, Laura and Shinaza, can you please bring your own shares in? And if you have questions for Chanzu and Lisa, bring them in the chat. I mean, like, you do use the opportunity that the chat gives us to have this discussion asynchronously, eh?
Oh,
and you can always go back to their presentation and watch it. You want to say something,
that's what
Lisa?
we wanted to tell. We are going to upload it on Canvas, and you can see like the conclusion on all the conditions we did, and also see some limitations that Nango also has.
Yes, please, and let's have a discussion there if we so feel like it. I mean, it's a discussion thread anyways. So sorry for cutting you short, but let's keep tidy. Have a good time. So I had a fantastic time. I hope that everybody is having a good time. So short-term plasticity, Shinaza and Laura, we're ready for you.
Yeah, good morning, everyone, and welcome to our presentation. We'll be covering short-term plasticity and discuss a model, amongst other things. So first, we'll be covering the chemical synapses, how action potentials work, how vesicles work, how they fuse, the types that exist, replenishment, the types of plasticity, and a model to discuss that.
All of this in 15 minutes or 12.
Yes, we're trying.
I'm going to start with the basics of chemical synapses. So chemical transmission involves the release of neurotransmitters, and neurotransmitters carry the information from the presynaptic neuron to the postsynaptic neuron. They carry this through the synapses, as you can see in the images on the screen. So when an action potential or nerve impulse arrives at the action terminal, it activates the voltage-gated calcium channels in the cell membrane. And so calcium has a higher concentration outside the neuron, and so it rushes into the cell. So the influx of this calcium ions triggers the release of the neurotransmitters from the synaptic vesicles, and this goes into the synaptic cleft and through a mechanism called exocytosis. So the neurotransmitters diffuse across the synaptic cleft, and they bind to receptor proteins on the postsynaptic cell. So it's important that you know that the synapse can only function if the signal can be turned off. So once the signal is terminated, the postsynaptic neuron can return back to its resting potential. So in order for a signal to be terminated or end, the synaptic cleft needs to get rid of all the neurotransmitters that it has in it. So the neurotransmitters can either be broken down by an enzyme, they can be sucked back up into the presynaptic neuron, or they can diffuse away from the synapse. We have learned before that action potentials are an all or non-response, so they can happen at either full strength or not at all. But however, synaptic signaling is more flexible. So this means that in the presynaptic neuron, it can increase the amount of neurotransmitter that it releases when an action potential arrives. And the postsynaptic cell can also alter the number of receptors that it has on the membrane. Because the presynaptic and the postsynaptic cells can change their signaling behavior based on their internal state, this is why we say that the synapse is plastic. And we refer to this process as synaptic plasticity. So now Laura will continue on into the types of vesicles that we have.
Yeah, so vesicles are organelles made out of a phospholipid bilayer, and they're made in the endoplasmic reticulum or the Golgi complex. And we've been talking about vesicles in general, but there actually exist 4 distinct types of vesicles. So we have transport vesicles that work mainly within the cell, and those transport large molecules like proteins. And we have lysosomes, which move debris, waste products, harmful products, bacteria, and they also break down cells that are ready to die. Then peroxisomes have kind of a similar function, but they work with oxygen and they're mainly present in the liver and in the kidney areas. And then the secretory vesicles are the ones that we've been talking about here. They're used to store neurotransmitters and secrete them when needed. So they are ready, for example, at the membrane, and they can secrete those neurotransmitters into the extracellular area. But how do these vesicles actually fuse? The vesicles work with a different several proteins. So that's the snare hypothesis, which says that you have the T snare and the V snare. The T snare is the target snare, which is a protein that is present on the cell membrane. And then the V snare is connected to the vesicle itself. Then the G proteins, you can see the GTP and the Rab proteins, are used to facilitate, regulate, and transport the vesicle to the membrane. Then they kind of open up the vesicle when it connects. We also have 2 types of attachment. We have the kiss and run and the full-blown attachment. And you can see on the top right image that it only opens for a little bit, and that's the kiss and run one. So it opens up like a pore, which is called a porosome. It releases it, and if it fully incorporates into the membrane, that's called the full-blown connection.
So now we'll move on to vesicle replenishment. So what is replenishment? The Google definition of replenishment is a restoration of a stock or supply to a former level or condition. So if you use this definition that we know of replenishment, then vesicle replenishment would be returning the amount of vesicles back to the original number. So vesicle replenishment depends on calcium ions, and this influx of calcium ions is regulated by the membrane potential. So what happens after vesicle fusion is that the neurons must replenish their stock so that they can be ready for the next action potential. And the replenishment process is known to involve a fast calcium-dependent pathway and a slow calcium-independent pathway. So a protein called calmodulin binds calcium ions is important in this calcium-dependent pathway. So in a study by Liu et al., they found another protein called synaptotagmin 7. They found that it has a role in replenishment of vesicles. So we already know from the synapse lecture and the brainskip cards that synaptotagmin is a calcium sensor that's involved in vesicle fusion. And so synaptotagmins are a family of proteins that are involved in synapses. And there are 3 of them, synaptotagmin 1, 4, and 7. So in their study, they found that calcium binds the synaptotagmin 7 and the calmodulin, they bind to each other and they form a complex. And this complex is the calcium-dependent replenishment pathway. So short-term plasticity, that's important in the central nervous system. It changes the vesicle, synaptic vesicle probability. It's readily reducible pull size, synaptic vesicle replenishment, and synaptic vesicle recycling. These 4 things can all impact short-term plasticity. So for example, the replenishment of the synaptic vesicles in the readily releasable pool plays an important role when we determine the rate and degree of the short-term plasticity for example, for depression. But later on, we will talk about the short-term plasticity. So in conclusion, for the vesicle replenishment part, the Leo and others, they discovered that synaptotagmin and contributes to short-term plasticity by regulating synaptic vesicle replenishment. And this is what we call the calcium-dependent pathway. But however, it's not exactly known how synaptotagmin and calmodulin, how they actually regulate this synaptic vesicle replenishment. But we know that they're involved in this process. Now Laura's going to continue on with the short-term plasticity.
Yeah, so for plasticity, we have short-term and long-term plasticity, and we're covering the short-term plasticity that can be further divided into short-term depression and short-term facilitation. And the depression means that there's a decrease in response from the postsynaptic cell, and the facilitation means that there's a rapid activity-dependent change in efficacy. So some cortical areas can be either depression dominant or facilitation dominant, but there can also be a mixture of both. And when we're talking about short-term plasticity, we really mean short-term. So it can be hundreds of milliseconds up to seconds. And it can also quickly return, the efficacy can quickly return back to baseline level if it stops right there. And the plasticity is dependent on calcium ions. So for facilitation, the calcium influx determines the synaptic strength and the release probability, and also the consumption of the readily releasable pool. And it's also abbreviated by RRP. So the RRP is a bunch of vesicles that is waiting at the cell membrane that is, as it says, ready to be released. And you also have the residual bulk, which is way smaller in amplitude and will be depleted later. And the depletion of neurotransmitter that is used also determines the amount of synaptic plasticity and facilitation.
So before we go into one of the models of synaptic plasticity, we should look at the main things that happen when an action potential reaches a synapse. And then from this, we will identify the variables that are in models. So you can see in the figure above what happens when an action potential arrives. So the active zone is the site where the synaptic transmission of neural activity starts. So here you can see the vesicles containing neurotransmitter and proteins are clustered together and they're ready to be released. The release of the neurotransmitter from the vesicles at the active zone, this starts when the voltage-gated calcium channels open and then calcium enters the cell. So the intracellular calcium concentration increases. And then this rise in the levels increases the probability of vesicle fusion with the cell membrane. And so neurotransmitters are released into the synaptic cleft. So if you put together this knowledge that we have now, the release probability will be the first variable required in the model for short-term plasticity. And you can see in equation 1 on the left side, this is represented by P bracket T in the equation. It's the previous slide. It is important to note that the relationship between the intracellular calcium concentration and release probability is nonlinear. And you can also see from the equation P bracket T that the release probability is expressed as a function of time. And this is because that the probability of vesicles to be released is activity dependent. In the figure, you can see two different vesicle populations. So some vesicles are close to the cell membrane at the active zone. This form the releasable pool, and the others are held onto to replace the neurotransmitter release. So these form the reserve pool. So these coming after the ones at the active zone are released. And so following on from this information, the second variable and in synapse models is the number of vesicles available for release. So this is represented by N bracket T in equation 1. So to summarize what I just said so far, the vesicle number and the release probability are the key variables involved in models of presynaptic transmitter release. As you can see from equation 1 on the left side, T bracket, capital T bracket small t is the amount of transmitter released into the synaptic cleft at time t. So in other words, the amount of transmitters released into the cleft is determined by the probability of vesicles to be released when there's an influx of calcium, multiply the amount of vesicles available to release from the active zone. The chance of this happening is all activity dependent, which is why the term is expressed as a function of time. Since we have 2 minutes left, I'll move on to the model of STP. So the model represents vesicle depletion as the main cause of synaptic depression. So in the model, they assume that they did like a tectonic stimulation on a neuromuscular junction, and they said that the continual stimulation will reduce the number of available neurotransmitters, and this will lead to postsynaptic response. And this process is shown in equation 3. So NT is the release pole occupancy, and this is bounded between 0 and 1. Tau R is the time constant of vesicle replenishment, and TJ is the presynaptic times. In this model, they concluded that there is an exponential decay of the postsynaptic response when stimulated as a constant rate, and that there's an inverse relation between input frequency V and the steady state level of depression. With this model, they found that it doesn't fit. They found that it fit responses recorded, but they also found that sometimes sinuses showed deviations. And you can see from part E, this shows that the steady state response is inverse to the frequency. Yeah, you can see this inverse relationship, and Laura can just conclude.
Yeah, so to conclude, the goal of this presentation was to explain how vesicle dynamics lead to short-term plasticity. We've covered how the action potential works, how vesicles fuse, the types of vesicles that exist. We've also explained a model that showed that the amount of vesicles ready to be released and the release pool probability are variables that affect the short-term plasticity. So for example, synapses with a larger vesicle pool also tend to have a higher release probability. So facilitation is expected to be dominant at smaller synapses.
Here's a very short question to wrap up. So what kinds of things can be learned with this type of short-term plasticity? So what's it used for in the context of cognition?
For learning and memory?
Yeah, clearly. But do you have a more concrete example? Next presenters can already start to join in, as you think. We can also take this discussion into the chat. But in general, if you don't want to do what you've just done, synaptic depression by vesicle depletion is a great way to go about it. So if you're wanting to create sequences in Hebbian learning style, you don't want to keep the stuff that you just had active continuously active. You just want to go for the next new thing. That's one way in which you can create cell assemblies also in the hippocampus. Just wanted to add this, what does this mean for the other level? Now let's go for the next one, shall we?
Hi everyone, welcome to our presentation about axonic propagation. The final goal of our project is to explain a model of the nodes of Ranvier and to show what neurons gain by adding myelin. We will start with a brief clarification on the main concepts, followed by our model. Then we will show you the dependence of the propagation speed by changing the axon diameter and the myelin thickness. And we will end with a general conclusion to answer our goals. So let's start with a clarification. When we talk about axonic propagation, we talk about the propagation of an action potential through the neuron's axon. And this can be deviated in unmyelinated axons and myelinated axons. Unmyelinated axons contain sodium, click. Next slide, please. Yes, unmyelinated axons contain sodium and potassium channels uniformly distributed over their entire length. When an action potential is fired from the axon helix, sodium channels further down the axon, which were previously closed, will start to open, thereby depolarizing the membrane. And in unmyelinated axons, the action potential propagates in a linear fashion, while in myelinated axons, the sodium and potassium channels are only in the internodal spaces, so it's between the myelin sheets. As our action potential travels down the membrane, sometimes ions are lost as they cross the membrane and exit the cell. The presence of these myelin sheets makes this escape really hard and so helps to preserve the action potential. A myelin sheet also decreases the capacitance of the neuron. Since a neuron has a negative membrane potential, it's got a lot of negative ions inside. it's got a lot of negative ions inside with no positive ions nearby to balance them out. This makes the negative ions attract positive ions outside the cell. However, where the myelin wraps around the cell, it provides a thick layer between the inside and the outside of the cell. So fewer negative ions gather at these points because it's further away from the positive charge. Now there are parts in the axon that are still negative, but contain proportionally far fewer negative ions. This means that as the action potential comes rushing by, it is easier to depolarize these areas. So it decreases its capacitance. The spaces between the myelin sheets, next slide please, yes, are known as the nodes of Ranvier. And these nodes are the only place among the axon where ions are exchanged via the ion channels. As sodium rushes into the axon, it creates an electrical force which pushes on the ions that are already inside the axon. This rapid conduction of electrical signal reaches the next nodes and create another action potential. Thus the signal gets refreshed. This allows the signal to be propagated over a long distance at a high rate without the degradation of the signal. And this process is called saltatory conduction. A second way to speed up a signal is to increase the diameter of an axon. Next slide, please. Larger diameter axons have a higher conduction velocity, which means they are able to send the signal way faster. This is because there's less resistance facing the ion flow. We have a lot of ions floating into the axon, so the more space they have to travel, the more likely they will be able to keep going in the right direction and won't bump into things like the proteins or vesicles. And next slide, please. To get a little bit more feeling for this, we will give you an example. Imagine you are walking and suddenly you trip and begin to fall. Luckily, your body senses that your limbs are in the wrong place, and instead of falling to the ground, you just stumble a bit. This sense of knowing is known as proprioception, and these signals are among the fastest in your body. And why is this? Because they have a large axon diameter and they have the myelin sheets. And that makes it possible to send the signal at rates of 80 to 120 meters a second.
Okay, thank you, Jacobine. Now that Jacobine has explained which kind of features make axonic propagation go faster, I will explain the model that we have used to simulate a myelinated axon. Take a quick glance at the formula, but I will explain first the variables and the parameters. L in this formula is the internodal length, so the length of the nodes and the myelin part segments. RL is the longitudinal resistance. This is the resistance that the current faces when it propagates through the axon per length. C is the capacitance of a node or myelin part. UN is the voltage of segment N. So UN plus 1 is the voltage of the next segment, and UN minus 1 is the voltage of the previous segment. Ion is the ion flow through the ion channels, so the sodium, potassium, and Lie current. The ion flows are determined by the formulas of the Hodgkin-Huxley model, so also by the gauge variables M, N, and H. However, we won't discuss those. We will only discuss this formula. As you can see, we look at the formula, we see that the capacitance is multiplied by the change in the voltage of node N over time. And this change in voltage of node N over time depends on 1 divided by L times the longitudinal resistance. This is the total resistance that the current faces in one node. So it's logical that we divide by that, because the higher the resistance is, the less the voltage changes and the less current propagates through. Times this term. This term gets more logical if you look at like that, like this. We see it's the voltage of the next node minus the voltage of the current node plus the voltage of the previous node minus the voltage of the current node. And this is very logical, because if the voltage of the next node is higher than the current node, then voltage from the next node, current from the next node, flows to the current node. The same goes for this one. If the voltage of the previous node is larger than the voltage of the current node, then voltage goes from the previous node to the current node. Also the other way around. If the voltage of the current node is higher than the next node or than one of the previous node, then the voltage decreases because voltage propagates from the current node to the next node or the previous node. Lastly, we have to subtract the sum of all the ion flows because in the nodes, the ion flows make sure current leaks out or gets out of the node, and therefore we subtract by the sum of all the ion flows. And we use the Euler method to update the nodes in these with this differential equation. Now, how did our model look? We divided the axon in alternating segments of 90 parts of myelin segment and 1 node of Ranvier. So we start here at the axon hillock, that is 1 node. Then we have 90 nodes of myelin because the myelin sheaf is substantially longer. Then again, 1 node of Ranvier, then again 90 nodes of myelin, and then again 1 node of Ranvier. The myelin segment is different from the nodes of Ranvier, that it has a smaller capacitance and there are no ion flows. We then inject a current for 5 milliseconds and we continue our simulation without a current for 35 milliseconds. Let's look at what happens. Here we see the axon hillock and the nodes. The nodes are red and the myelin parts are blue. And let's zoom in to have a better look. As we can see, we inject a current, which increases the voltage and results in an action potential and in a spike. This spike gets propagated through the myelin segment and decreases the further it gets in the myelin segment. You can also see that the second spike is caused, but I will explain that one later. So let's focus on the first spike for now. This first spike gets decreased, but still is enough to cause an action potential in the next node of Ranvier. This action potential again gets propagated and decreases, and results in a next action potential in the next node of Ranvier. However, there was also a second spike. This second spike is back propagation. Because this action potential is so much larger than the voltage in the previous node, also voltage propagates back to the myelin segment, and that is what you see, the second spike. So the second spike also gets propagated back for the first node and decreases, and is not enough to cause a new action potential here because this axon hillock is still in its refractory period. This is also what we can see here as the first node. This is the first node, this is the 5th myelin segment, the 10th myelin segment, and the 15th myelin segment. You see that the voltage decreases. Then we get another action potential in the red, and you see that the back propagates to the 15th, the 10th, and the 5th, and then they reach equilibrium. We wanted to find out what happens if we decrease the diameter. So what we did, we decreased the diameter of the axon, and this on its part increased the longitudinal resistance. So we multiplied the longitudinal resistance in our model with 1.5. And as we can see, the propagation of the action potentials takes longer. So these are the nodes of Ranvier. The second node of Ranvier takes longer to get an action potential, and the propagation goes less far. As we can see, the third node doesn't even reach an action potential anymore. So a smaller diameter increases the longitudinal resistance and therefore decreases the speed and the length of propagation. And now we decrease the myelin thickness because we also wanted to see what happens if we do that. If we decrease the myelin thickness, we increase the capacitance. And as you can see, if we increase the capacitance, again, the propagation takes longer as it takes longer to get to the second spike. And it also reaches less far, as we can see that the 4th node is not able to reach an action potential anymore. And the nodes here are all the nodes of Ranvier. So again, if we increase the capacitance, propagation takes longer and reaches less far. So what is our take-home message? Adding myelin increases the propagation speed in long axons and how far the propagation reaches. The action diameter, increase in action diameter lowers the resistance, so there's faster propagation. This is of course logical. If there's lower resistance, ions can flow more easily. And the thickness of the myelin sheath, the myelin decreases the membrane capacitance. The The thicker the myelin sheath, the lower the capacitance, the faster propagation. Also, this is logical because if there's lower capacitance, a node can store less charge and therefore more charge or more current flows through the nodes. Yes, and so we have shown what an axon gains by having myelin sheaths, and we would like to hear your questions.
And the beautiful thing is that it was perfectly timed. So this was glorious. Excellent. Now I hope that there will be some questions. Questions, please. There are 3 minutes for questions. How about what happens in insect axons? Are they myelinated?
I don't think so because they are very small, but I'm not sure.
They're not myelinated. And
Yeah.
that's what, you know, insects can only work because they're small.
Yeah.
Yeah, the bigger the insect, the slower it is. Like the real propagation is then deferred to actual spiking. There's a lot of ganglia. If you really want in insects that are very long, if you want to propagate the signal to a very long pathway, you usually have segmental little nuclei that have the job of the nodes of Ranvier by amplifying the signal as they go. So cool stuff. Excellent. So it's one of the last 2 projects. I don't know if you've noticed the relationship. They were computational neuroscience projects rather than neurocompetition. I think it's nice that we have a mix between them. And the next one is going to be as well. So we have 1 minute for our next one. So Ine and Jacobine, excellent job. Like really cool stuff. Shall we go forward then?
Okay, thank you.
Chinaza also mentioned perfect time management. Indeed. All right. Please vote. And as soon as I notice that the numbers I have saturated, I'll flip this slide. We ready, Kate, Constantine?
Yep. Okay, can we go?
Yeah, we're ready.
All right, let's go. Well, we've got a lot to go through, so let's buckle up. Our project is based on a certain paper written by a couple of authors who made a model which is homeostatic and arrives from the central dogma of biology based on ion channel and gene expression. Next slide.
So let's break down this title. What again means the central dogma of biology? Just a little refresher. We move from DNA to mRNA and from mRNA through translation to a protein. A protein in this model will actually represent an ion channel. Ion channels, of course, led through ions and thus represent conductance. Thus, in our model, the essential link you need to understand is that mRNA levels represent conductance. Next slide.
Okay. The differences between the models, as Mario said, most of the previous models we had were abstract models, more of a neurocomputation model, which use weights and vectors to signify the change in the way these neurons spike against each other. But our model is more biologically based, it's homeostatic, it's more of a computational neuroscience model. It uses ion channel expression, the density of it, to signify the change in conductance. Also, the more abstract models do not really use or do not really have any compensation of the neurons and do not explain the different kind of cell types, that just encode them as being different. And ours does actually explain the set points certain neurons have, explain the way they can compensate, and explains how different cell types can come to be. Next slide.
So the homeostatic model, let's break it down into 5 steps that we'll go through. We'll start at the simple model of ion expression and take you through each of these. So simple, of course, is relative. So we'll start at the conceptual level. As I said, this is based on the central dogma from a gene to mRNA to ion channels, which mean conductance. So as you can imagine, because it's homeostatic, our model includes time, and mRNA and ion channels, of course, are synthesized at certain rates in time. This synthesis rate is important and will be referred to with an alpha symbol. Of course, mRNA and ion channels also decay in a cell at a certain rate, which will be the degradation rate. On the right, you can see a schematic depiction of how these rates will be incorporated and how mRNA can be translated into a protein or actually degrade. The main ion channel which we'll be focusing on will be a calcium 2+ channel, because this calcium 2+ channel is voltage dependent, so it's a good representation of electrical activity. It has buffering mechanisms which flatten out nice averages across space and time, and it is also known to regulate many other channels in the long run. Next slide.
Okay, the formulas we'll be using. The first formula I'll be showing you, the first line next to formula, is the formula for mRNA. As you can see, mRNA is partly made by getting the synthesized function and subtracting the degradation rate times the amount of mRNA you have presently. The same goes for the channel, only in this time different kind of rates are of course used. One's one that signify the degradation rate and the synthesizing rate of the channels. Next slide.
So let's expand this formula a bit to make it more biologically plausible, because we know that certain transcription factors and enzymes are actually calcium 2+ sensitive. So we've added this orange T in the little formula, which you can see represented in the table, which will be a calcium 2+ sensitive enzyme. This enzyme or enzyme group will regulate the production of mRNA, as you can see in the second line of the formula. The T has also been added there. Another thing we added here is in gray, the calcium 2+ intracellular level or concentration. And the T has its own synthesis and degradation rate once again.
All right, well, I'll take you to how the system then works with a little graph. It's good to note that the Ca2+ in the formula is not really just the intracellular calcium concentration, but it's actually the calcium concentration minus the target calcium concentration the cell would like to achieve. So in the little graph to the right of the slide, you can see a moment in which the target concentration the cell has does not equal the concentration it has currently intracellularly. This means that the transcription factors will increase as they would want more gates. The transcription, or the T, would then of course make more mRNA, as you can see by the sign line rising in the bottom right. This will of course then create more channels, as mRNA are the blueprint of the channels, which as you can see then follows by the blue line. This will again create more channels, create more conductance, and make it so that more calcium is able to get into the cell. This will also create a bit of an overshoot, a bit of hyperpolarization, only the other way around, which will then have to be accounted for by again slowing the mRNA production, after which it will slowly fluctuate around the target concentration it would like to achieve. Next slide.
So we now have this quite plausible formula, but let's simplify it a bit. Instead of using the orange T, we will be removing it and integrating it to allow two new variables. In pink, you can see the Greek letter tau. We have a tau y, which will couple gene expression to the concentration of Ca2+. And we have another pink tau, tau g, which will be a time regulation constant for channel expression, which you can see added in the bottom of the formula. The other thing that's added here is in red, the calcium 2+ target value that Constantine talked about. So now we have this simplified, but still biologically plausible and very realistic formula, which we'll be using throughout the rest of this presentation. So in order to see this in action, you need to know that we won't just be focusing on calcium 2+ channels. Actually, there are many calcium 2+ channels. For example, you can see here transient and slow. And in the table, you can see all the channels that we'll be using and following in this model and tracing. So let's zoom out a bit. You can see a graph here with on the x-axis time, and on the y-axis, you can see conductance measured in microsiemens. So we see all the channels that we'll be tracing, and each channel will have 20 simulations. At the start of the simulation, at the very left of the graph, these 20 simulations will start at random values, and throughout time, you can see that the model with the formulas we just talked about is actually able to self-regulate itself to a steady state of conductances. All the conductances converge, as you can see, to certain points on the right. And if you look at the top, you can see the phenotype changing, and all the way to the right, we have achieved a steady state bursting firing neuron. So let's move down a bit in this image. Something very important here that we can see. This is a very complicated graph, but you can see in pink the distributions of the conductances plotted against each other. So on the x-axis, you have certain conductances, and on the y-axis, you have certain conductances, and they've just been plotted against one another. In green, you can see the very same, but instead of conductances, it's using firing properties such as frequency or amplitude. What you can take away from this is that we drew straight lines, as you can see. These are all sort of linear correlations between the distributions of conductances and firing properties. So this sounds complicated, but what does it mean, Konstantin?
Well, this means that the conductance densities are firing properties and are showing pairwise linear correlations. It means that the ratios of the ties, the tau i's, basically are a rough expression of a rough estimate for the expression of genes. That means that the ratio of taus affect the conductance correlations, which will then define the electrophysiological properties of the cell, which will mean that basically the rough gene expression will affect the type of cell you have as it affects the way it fires. This means that changing the tau ratios changes the cell types. Next slide. This means that we can generate, by basically changing the gene expression, we can generate different types of cells. In this model we had generated 5 types of cells: a type 1 spiking neuron, type 2 spiking neuron, a rebound burster, a bursting pacemaker, and a tonic pacemaker. Next slide. Okay, now that we've got the cell, we can finally start by making networks. In this little paper, they made a certain network, which is based on the pylorus, which is basically just a circular muscle which divides the stomach and the colon. This model is very simple and only made up of 3 simple neurons. One is a pyloric dilator, a second one is a pyloric cell, and the third one of a lateral pyloric cell, and the third one is a normal pyloric cell. Next slide.
So they did a little experiment with these 3 neurons in a network. As you can see, the neurons are connected through green and red wires. These are all inhibitory connections. One is glutamate, one is acetylcholine, and one is fast inhibitory, one is slow inhibitory, respectively. And we'll divide this experiment into 4 little steps. At the start, random values for the conductances were chosen once again, just like before. This means there's no spiking activity, of course, because the conductances are set at a random point. So at 1, there's no activity. Then as we give it a little more time, you can see it achieve steady state, because once again, the conductances will self-regulate to this nice steady state. And at 2, you can see a triphasic firing pattern from blue to orange to purple. At step 3, we actually do something experimental. We hyperpolarize the blue pyloric dilator neuron by a current of -80 millivolts. And it's now suppressed, as you can see. The line is just flatlined. There's no activity anymore from the blue neuron. But then when we give it a little bit of time, as you can see on the right side of this image, the conductances will change after this perturbation, this experiment that we did. And the network will be able to self-regulate back to its steady state. At number 4, you can see the blue neuron firing again.
All right, we did try our own simulation by making code. We delved into the projects, but I'm afraid the project did not quite have the type of code or the type of the conducting background that we would like, as it used mainly gating variables, and we really tried to get behind the conductances. This means we had to use the provided code, which we had to search for, which was a lot harder than it would seem. They don't really present it in any normal way. And when we finally found it, we noticed that it wasn't in Python, but in MATLAB and C++. Us being both medicine students, we don't really have a coding background. So once we tried to manipulate or add anything to the code, it mainly ended in a total disaster. But we did manage to understand the code, and we did manage to run the tests by using a certain Excel sheet, in which they put all the variables and stuff they used. As you can see, next to this, on this slide, we made a little graph of our own. Next slide.
So let's move on to the final part of our presentation, which is the most interesting to us: compensation and pathology. As we saw before, our networks were self-regulating to small perturbations in hyperpolarizing currents. But what about things like missing channels due to certain diseases or medications, or larger perturbations? So let's take a look at this.
Okay, compensation and pathology. Here we have a little slide. We have 3 columns in the graph. One column shows, the first column shows the wild type on the left. It is just normal firing, how the neuron should react normally. In the middle column, you have the acute deletion of the channel, basically how the neuron reacts immediately after deletion of a channel. And the third column basically shows it, the neuron after a bit of time after deletion, in which it has been given enough time in which it should be able to compensate. Next slide. With this experiment, we were able to find that cells react quite differently to deletion based on their conductances. The first type of cell, like cell A, is sensitive to deletion. As you can see in the middle column, it stops firing right after deletion, but it does manage to compensate. And the third column, you can see that it starts firing again and it has the same type of firing. In B, in experiment B, we basically found that in the same population, variability in sensitivity to deletion varies. As you can see, 2 of the normal types of cells have been taken. Both have been a certain channel have been deleted, but only one of them is sensitive to deletion. As you can see, only one of them stops firing after deletion. Both of them did manage to compensate. Oh, thank you for the next slide. Then we've had a little cell C, which is a cell which was sensitive to deletion and did manage to compensate, but it compensated pathologically. As you can see, at first it's a burst firing cell, but then it turns into a tonic firing cell, meaning that the intracellular properties of the cell have changed, which is not something you generally like. In test D, you saw a cell which is very robust against deletion. It might have a slight change of frequency, but then it also compensates for that. So it just doesn't carry the cell. And so E, it's a cell which is robust to deletion. As you can see, it just keeps on firing after deletion, but then it suddenly stops at compensation, meaning we have another pathological compensation mechanism right here. Next slide.
So the main takeaway you need to know from this is that compensation can actually be pathological. And this was compensation to deletion of ion channels. Here we wanted to explain what happens when we apply larger perturbations. Doesn't really matter. What you just need to know is that cells are able to become more robust to these perturbations by changing their taus once again, the tau ratios. So the tau ratios not only define different cell types in this model, but are also able to change to make the cells more robust. So this actually is very interesting because it can have many possible applications in the future. We can use it in medicine to study pathologies or medication. And of course, in neuroscience, we can just generally help us understand and make other models more biologically plausible, which will be very interesting. And we can maybe see how gene expression or these tau ratios change over the course of a cell's development, differentiation, or lifespan, which will be very interesting indeed. That was our presentation. We'd like to thank you for your attention. Maybe you can ask any questions that you might have.
I just wanted to share that this is the future of neural networks. Every neural network we've been making so far that is computational neuroscience-like, it's stiff. Every model is tuned to a particular firing rate with specific conductances. That's not like the brain. The brain has a bunch of neurons that change up and down. And this is one of the first, and you've explained it beautifully, I have to say, even though you weren't able to run the C++ and MATLAB code. And I kind of knew there was going to be a little bit tough, but you produced a plot, so it's something. And it's definitely the future. I think that we want even our artificial neural networks to be more robust and more changeable. And I think that this is actually upcoming. There was a paper just published couple of weeks ago talking about liquid artificial neural networks, and they deal with different taus. And it's the first time that the taus are basically being used to produce time series. Is a recurrent neural network type of neural network. So cool stuff developing in that direction. We're managing so far, so it's 11:05. I wanted to keep managing, and so we have now a 5-minute pause, and yeah, we can take discussion to the chat, and we meet again at 11:10. All right. So thank you so much. We carry on. I'll be back in a moment too. In the interest of punctuality, Lucas and Jelle, you're welcome to start the presentation. People will be joining in. If they miss your first sentences or two, they can always go back to the YouTube video that will be available.
Okay, is everything working? Am I?
No, it was, but now it isn't.
Okay. Just a sec, I'll try again.
Now it is.
What about now?
Good.
Okay, so I hope everyone's back. We're just going to start. So our project is about backpropagation and biologically plausible alternatives. Let's get started. So we'll do a really quick refresher about how exactly backpropagation works. And the image here is a really basic neural network. All the connections between the neurons have a certain weight. All the neurons itself have biases. You feed the training example through the network. The network spits out a number between 0 and 1 in most cases. You tell the network how it did with the cost function, and then backpropagation works with the negative gradient, starting from the right, propagating back through the network. Backpropagation in the brain. First question we must ask is the brain similar to a neural network? And if so, what kind of neural network is it similar to? Because there are a lot of different types of neural networks, and all these different types use different kinds of backpropagation. The type of neural networks we discussed mostly up to this point are simple feed-forward neural networks. Information goes into one side of the neural network and comes out the other side and goes through the network layer by layer. Each neuron in the network is only connected to all the neurons from the previous and the next layer of the network. The brain obviously is a lot more complicated than this. Real neurons are not nicely ordered in layers, but have connections that go in all kinds of directions. So obviously, this means the brain is not a feed-forward neural network. So vanilla backpropagation is not going to work only because of this reason. Also, for vanilla backpropagation to work, information needs to go through the neural network all the way. And on the other side of the network, the neuron reflects on itself with the cost function, and then the weights and biases are adjusted started from the back. In a neural network, the information can pass through the neurons in both directions. This is not possible in real neurons, so this is another reason why a vanilla backprop most likely won't work in real brains. One thing is for sure, we're going to need a different kind of neural network if we want to get closer to how backpropagation works in the brain, if it works at all in the brain. Recurrent neural networks already approximate how brains work a lot better. So what are recurrent neural networks? In their most basic sense, recurrent neural networks connect the outputs of all neurons to the inputs of all neurons in the network. When everything is connected, these are fully recurrent networks. Not everything has to be connected necessarily, but that in its most basic form is a recurrent neural network. As I said already, this is already a better approximation of real brains because not everything is organized in strict layers, but the connections go in all sorts of directions. Another step that can be taken to take this particular model closer to how real brains work is the way the information is conveyed. For example, in normal recurrent neural networks, the information is conveyed in bits and numbers. But if we take a recurrent spiking neural network, the information is conveyed in discontinuous and asynchronous spikes instead of bits and numbers. So we now have a neural network that approximates the human brain a lot better already, But standard backprop does not work in recurrent neural networks because standard backpropagation, first all the information has to go all the way through the network. Then starting from the back with the negative gradient, it works its way back through the network. So we're going to need a different kind of backpropagation. And Jelle is going to say a little more about that now.
You're muted.
I'm sorry. We saw the recurrent neural network at Lucas' slide already. So how do we apply some form of backpropagation to this neural network? Well, the most used method is the backpropagation through time. So of course, the neurons are connected to each other, and they send signals one after another. And if you unfold this in time, you get basically a virtual feed-forward neural network, to which we can then apply normal backpropagation. So you have the feed-forward neural network. It works the same as the normal backpropagation, except for this time it works, every layer are the same neurons, except instead of different neurons for each layer. This is also possible for spiking neural networks, but it just uses a few different kinds of derivatives. What doesn't work is this in the biology, because some of the same arguments we had against normal backpropagation. It requires storing of all the intermediate states as well. So for each neuron, because every layer is the same, uses the same neurons, you have to store each intermediate state of the neuron. And then only after the task is finished, it can calculate the error. And it has to transmit this error signal backwards through time for the different time steps this RNN has taken. Next slide, please. So one solution we found was in this paper, a solution to the learning dilemma for recurrent networks of spiking neurons. They found, started with two biological clues. One of them was eligibility traces, which means once a synapse has fired, it retains some indication that it has fired, such as a higher concentration of calcium ions or activated enzymes such as chemkinase 2. And the other clue were learning signals. So those are signals top down that inform the neurons of behavioral results. You can think of dopamine, acetylcholine, and other neurons firing as these kind of neural learning signals. Next slide, please. So what they came up with was this model of E-propagation, or E-prop in short, which uses a loss gradient that looks like this. It has more difficult mathematical equations as well, but this is the gist of it, which means that the gradient of a synapse, so the part before at the left side of the equation, that tells us how the weight should change in order to minimize the error of the network. And that is computed by combining the learning signal and the eligibility trace at a certain time point. So for each time point, we have the eligibility trace for that synapse, as we can see in the picture here with the blue arrows. And then at the time point, we also get some feedback, which are the learning signals, and those are combined to change the weights at that time step. This means that you don't need to unroll the network. You don't need to go backward in time to change weights and compute and start the learning process, which is of course preferable to unrolling a whole network and storing every every intermediate state of every neuron. Yes, I think, yeah, that's it. Then we go to the discussion. So e-propagation, as this sort of continuous method for learning, even approaches the learning ability of the backpropagation through times in recurrent neural networks, which is currently one of the most powerful learning methods for recurrent neural networks. All the while, this e-propagation uses biologically plausible mechanisms. Also, it uses less memory because you don't have to store the intermediate states, and it is less energy intensive. First of all, because it uses spiking instead of continuous signals, and you don't have to communicate every state to the memory and to store it and then bring it back for the error computation, which also costs energy. So this makes it also a nice candidate for hardware applications. Last fall, what the authors of the paper found, which was that this provides a hypothesis for a newly experimentally found observation. That's the dopamine signals to different populations of neurons also differ. So previous theories of reward-based learning, they say the learning signal is the same and sent to all neurons, but they found that there's a diversity of dopamine signals sent to a diversity of neuronal populations, and that's similar to the way that the authors of this paper made up their model.
Great, thanks Jelle, Lucas. So please vote for group 9. Here's a short question. What kinds of problems can this, so first off, I love that you talked about eProp instead of the solutions by Geoff Hinton or Roofsoma. So this is a very novel proposition, eProp, and I think it's very insightful. But here's my question. What kinds of problems can we train with eProp? I mean, do you have like an idea, like one nice model, one nice example of this? I mean, you told us like abstractly that it does like backpropagation through time, but what were the benchmarks used? What kinds of paradigms? How is it? How are they closer to, brain? Because that was the motivation in the beginning.
Yeah. So they did several experiments with this. One of them was phoneme recognition, which is basically recognizing words. For this, you would need some kind of time dependent recognition. And in this, it already came very close to the backpropagation. It also did several other tasks, mostly to do with temporal learning. What was your question again?
So that basically, so what paradigms did they train it on? Because why do we have a basal ganglia? Would be a good question. It's, we just learned that action selection goes through the basal ganglia, but we learn now that eProp can solve biologically plausible backpropagation. So why do we have such good anatomy in our brains, and why is it doesn't seem to be required for most of current recurrent neural network models, such as the one you presented? But I don't know if we have the time to discuss this. It depends on whether Ruud and and Nebi are ready to present or not, because yeah, are you? Amazing, sir. Thank you, Nebi. Like I understand I understood your complex scheduling problems such as mine. So thanks for being there at the right time. We can bring this discussion later also into the forum if you guys feel. And otherwise, as far as I am concerned, we're ready to begin. So group 9 is now online, so please finish voting. And let's have a look into our own TCB version of the neocognitron.
Okay, is everyone done voting? Okay.
Yeah, I'll change the slide when I see that there are 17 people at least, because so far that's yeah, that's the average number of voters.
Okay, perfect. So as you can see, we are going to talk about the neocognitron. First, we're going to tell you a little bit about it. The inventor, or the person who thought of the neocognitron, is Kunihiko Fukushima. He first came up with this idea in 1980. And why is this so special is the question, obviously. He wrote a lot of papers about it. And the reason why it was very special at the time is because it does not require any pre-processing, which is very useful, saves a lot of time. And also it is very well equipped for computer use, which also was quite special for the time.
So of course we're going to talk about a little bit about how the neocognitron actually works and what it is. Well, it basically is a hierarchical network that extracts certain features from input to actually recognizing what the input actually is. And of course it's hierarchical because the features that are extracted are going from less complex to a lot more complex. So in the beginning you start off with like edges or contrast, and in the end you will have like almost actual figures. There are a few different planes in the neocognitron that consist of S cells and C cells. The S cells are mainly used for feature extraction, and the C cells are mainly used for the space that they're in. So this is really important because this means that, yeah, exactly, layers instead of planes. The S cells extract a certain feature, and then the C cells will actually see if the feature ends up in the certain area that the C cell will be active in. Another difference between the S cells and the C cells is that there's a possibility to change weights. So from the C cells to the S cells, there's actually a change in weight of how important the input of the C cells to the next S cell is. And the S cells have an inhibitor, which actually means that when the activity of the C cells isn't high enough, the inhibitor will come in and say, well, oh, S cell, you don't have to do anything, we'll just move on without you. And another cool thing about the whole neocognitron is the training, especially since it's very old, and we ourselves made something with supervised learning, but the neocognitron can actually do unsupervised learning. This works as follows. In the beginning, the weight between the S cells and the C cells is basically 0, and the S cells don't really have a feature that they can extract. When you then give an image to the neocognitron, the S cells that respond the most to a certain feature in every single layer will eventually extract that feature, and then the next feature comes in with the S cell that responds most to that, and so on and so on and so on. And so in the end, you can also use unsupervised learning to actually recognize certain images. Of course, this takes a little bit longer than supervised learning where you give labels.
Okay, so what did we do with this information? Making a neocognitron was a little too complicated, especially since we both have 0 coding background. So we tried to make something that illustrates.
You're no longer allowed to say this. Carry on.
So we tried to make something that kind of shows what a neocognitron does without the exact advantages of neocognitron. So what did we do first? We acquired some data. We wanted to do this ourselves, but then Mario gave this brilliant idea of just using MNIST data, which is a huge data set with handwritten numbers, labels, classifiers. It's all already in it. So that was very nice. So we got that data, figured out how to get it into Python, which took long enough already. And then the second step was to convolute it. The convolution here works for us in a way that the C cells would kind of work as it kind of allows some differences in space and position, not as much as a C cell in a neocognitron would allow, but it helps. So it allows a little bit of deformation because it's a little more convoluted. Then we had to pick layers because obviously we don't have a nice S cell and C cell function that we could just pick. So we had to figure out what are we going to do. So what we did was we took 2 convolutional layers with a pooling layer each, and then a flattening layer, a dense layer, and a softmax layer. Don't worry, I will explain. So as I said, we took convolutional layers. The shape of the image was 28 by 28. So that's also the size. And then the size of the batch was 46. So we showed 46 images. 64, actually, sorry, 64. And then after it goes through the convolutional layer, it goes into a pooling layer. This is a max pooling layer. So what it does is it takes squares of 2 by 2 and it takes the highest value out of that square, and that kind of gives the maximals of each little 2 by 2 square and gives that as output, which is why the pooling layer is half as large, 14 by 14. Then it does that twice. So now the next convolutional layer is 14 by 14 and the pooling layer is 7 by 7. And then it takes a flattening layer, which basically takes the dimensions of all input before it and gives it 1 dimension or as many dimension as features that we're looking at. So in this case, it puts it basically all in a row. So it's very easy to take to the next layer, which is a dense layer. This dense layer basically makes sort of an inventory. It takes every single output from every single piece in the max, in the flattening part, and it takes every single output and puts it to 1 kernel. So every single kernel gets every single output, which means that it has everything in each of those kernels. Then the last layer is the softmax layer. It gives all of these kernels probabilities and takes the one with the highest probability and puts it forward as the output. This is very important in our process because it saves a lot of time because it basically chooses what is most likely to be the useful output here. So then, as you might have been able to tell, there's a few differences, but it all comes down to one thing. The neocognitron is far more tolerant. It allows some big changes in position. It allows way more deformation. It allows differences in size. This is all not applicable to us because, for example, we only had 28 by 28 squares. If the number was not within that square, it cannot recognize it. So in a neocognitron, this has way more allowance for these kind of differences and changes, which makes it also a lot more accurate and useful in practical application because obviously, if you're trying to find something, you can't always have nice 28 by 28 squares. So then the output of our network, it basically gave a bunch of correct predictions. Here you can see some and a few incorrect ones. As you can see above it, it says what it predicted and what the class label was. And you can see the nice little images.
Yeah, and as you can see, these are like all the pictures have exactly the same format, whereas in the neocognitron you could have, for example, the 7 on the left one could be in the corner and it would still be able to recognize the number 7, and here it will also be in the same place all the time.
So here we have some plots showing the accuracy and the loss that we got When training, as you can see, we were able to train it very accurately, 0.9975. So we would say that it is a pretty successful network. It was very well able to recognize these numbers, obviously in the condition that they fit the exact position and size that we needed them to.
Well, I will add something to this because I see it's not in the graphs, because the x-axis resembles the amount of epochs that we ran to train the network or test the network. And as you can see, is from the beginning onwards is already the accuracy is pretty high and the loss is also pretty low, but that's mainly because we use like very high, just a huge amount of data already.
So what are some of the limitations that they gave for their own research for the neocognitron? Well, it was that the quality of the training set is very important, which is also applicable to what we just said. You have to pick the training set very well. If the training set is not good enough, not big enough, not specific enough, the neocognitron will work less well. So they said that a big reason for their huge success was because they took a lot of time finding the perfect training set. Besides that, lesser performance was found with unsupervised learning. This is kind of logical because obviously you can't manually change the weights and perfect them. And then last, they said that only lines of 1 pixel width were used in their preset data in their training set. So it was only recognizing lines of 1 pixel as handwriting. But these are obviously not huge limitations. They don't take away anything from how useful and interesting this idea is. And yeah, we think that the neocognitron is very useful and very cool still to this day. A very cool idea.
40 years later.
Yeah. So here are some of the sources we used. And then if you guys have any questions.
I'm going to shoot one since we have 3 minutes. How to make a network positional and size invariant. So basically how to make a network recognize smaller numbers, for example. Your network, is it possible? So what would you do in your network to make it recognize smaller numbers, for instance?
I think probably first off more layers, because we specifically didn't use that many layers because it was an easier pattern to recognize. And then probably.
How does the connectivity in these layers would look like? I mean, what motif would you find? I mean,
what do you mean by that?
Kind of like what type of network structure? If you want to find like size invariance, for example, basically a small number and a large number, how do the convolutional layers would look like? I mean,
yeah, I mean, you would probably need some sort of feedback, like to the previous layers.
You don't need feedback. I mean,
no,
but you do need to shrink like your you need to subsample the image on top. Ultimately, you need to truly shrink it and then search, like you said, more layers, but you would have to search in subparts of the visual field. So in principle, the visual field is the entire thing with the 5. I mean, one way to go about it is actually change the input. Instead of putting the making the number occupy the entire input space, you just make a bigger input space and put it in different places. And if you put in a convolutional layer with some sort of shrinkage ability, you will then find a little bit of size invariance. It's almost the same for positional.
We were already pretty impressed that this actually worked, and every time we tried to run the whole system, it already took like 20 minutes. So every time we wanted to change something, like a small thing, for example, the batch size or whatever, it still took 20 minutes to actually see what the difference was. So
yeah, no, for sure. That's why I was asking you, an intuition about how to solve it. Fabulous. So fabulous. please finish voting for group 10. I'm going to have a couple of final words now. And my word is this. I mean, like YouTube couldn't compete with these 10 teams today. I mean, like I have learned in 3 hours, like presuming I didn't know anything about it, I would have learned more in 3 hours than I would have learned in 2 months of the computing brain minor. It's really cool stuff. So thank you so much for your presentations. I do think they got the spirit of the idea. It was absolutely efficient way of transmitting the information. You will be able to come back to it eventually and review, play at 1.5 speed and get to some of the fundamental elements. And yeah, I mean, there were many opportunities for insight learning across the presentations. There were many opportunities to create some links. I hope you have had some new links. So this is how I wanted to wrap this. Now, tomorrow you have your exams, as you all know, and are trembling before. I suppose there is still time for you to go through all of the Brainscape cards. That's 400 something of them. The questions, like mostly, by and large, they are included in the Brainscape, and some of them are extracted from the learning goals of the Jupyter notebooks, as you might presume. But I would be very surprised if you were surprised at the kinds of questions you're going to get there. I will be curious, however, from your feedback after the exam is passed. So I can also report on what you think about yourself. So your peer reviews have a very strong median for all of the grades, which is about a 4. So considering that this is a 50% of your grade, the 4 out of 5, it's basically an 8. And so I'm not presuming, I'm presuming you're all going to be doing fairly well. So relax about the entire grade, because grades don't matter in the end. What matters is what you've learned. And next week, we have a overall feedback session where I would love to see all of you, just for us to have a chat, talk about the different projects, talk about, possibilities to improve the minor, like where should this go? Where did you learn the most from? What would you like to see more of? And so with this, we're going to be using your feedback to improve the next installments of the minor. I see that there's a message here. When is this session next week? Is in Google Google Calendar. Should be in Google Calendar. Is the last session, I think. I don't know by heart. So the exact location is still to be announced. Now, let me see. This is not the final big send-off. One more thing. You will be given the opportunity to give feedback to the course in a little form when the minor organization, the overarching people come to you and say, like, what did you think about your minor? I hope you've enjoyed it as much as I have. Like, I have enjoyed working with all of you, like, very, very substantially. It was, to me, like, I have TAs from past year and the minor. I think it's the 3rd year, so there's a lot of things that went better this year. And thank you, Neve. I'd like, really, like, go to the forum and say it, because that helps my career. I hate it, like, we live in the 21st century or 2020s, so we work with likes. The exam is in real life. I hope that you've been sufficiently informed by the minor, like you received an email, not from me, but from the people that are actually organizing this. And please, if you have any problems, WhatsApp or get out to me, but ultimately I haven't organized this, okay? So this is from the minor commission.
Mario,
yeah.
I have one little question. What is like the minimal grade that we have to get, like, for the minor? Is it a 5?
It's I think 120.
No,
I have no idea.
120.
So I think 6. I think it's 6.
And only for the exam, but
for the entire minor. So what's the minimum? Come on, Lisa, you're not asking me this
only,
question, are you?
not only for the exam, because like at
Yeah.
psychology, we have to like get a grade above like the 4.5. So, but I don't know.
4.5 out of 10? Yeah,
For
I
entirety
think the
you
minors,
have
so
to
this
get
is,
5.5s.
yeah.
For the entirety of year 3, you just have to get a 5.5 or above.
That's right. So this is a rule actually for all the minors. I also didn't institute it. But
We're going for the 8s, you know, like
yeah, exactly. At least, I mean, come on.
yeah, 9. You know, it's gonna be fine.
I hope that there will be some challenging questions, so you know, to distribute them around. I hope that there are no mistakes in my answers, but we will have a post check with false positives, false negatives, where I will see the statistics, and then I'll basically have the contributions from everybody. If there's a distribution of a grade and that grade seems to be odd, or most people didn't get like some sort of fundamental, I'm definitely going to go and analyze that. And there's a chance that we, that question gets either invalidated or judged in different ways. You will know. You can also add your feedback, I think, as you do the exam. It's in test vision. It's in real life, but you're going to be doing it online. So it's gonna have your own computer set up for this for you there. Don't know. Did you know this? It's not a sheet of paper. It's basically computer. But it's straightforward. I mean, it's basically test vision, and you can give feedbacks in the individual questions. So if say like, I have no idea about what you mean, I'll look into it, and depending on how the distribution of grades is, we will have some material to edit postdoc.
Do we need to bring a calculator?
Yes, you do. This one, the best calculator, I mean, like a pen and paper, like, come on. Like, can you multiply 2 numbers, Julian?
I sure hope I can.
And then sum.
And
then tell whether it's larger or smaller than another number.
Okay, that's
so if you can basically deal with multiplications of pairwise numbers. It's neural networks. There's nothing else than basically summing and multiplying. You definitely don't have to compute sigmoids in your head. No, of course not. No. I mean, like, I'm interested only in the conceptual knowledge. So no, you don't need a calculator. You can bring a compass if you want to draw a circle, but it will be on the screen of the computer. And I don't know if people in the minor will like that, because I won't see the circle you drew. It's a bad joke. Okay, guys. So I know that some of you have to leave, and unfortunately, like, given all the circumstances, so have I. This is not the final send-off. The final send-off happens next week. So for the moment, I just hope that you will have a great time in the last afternoon of preparation. I will keep Teams open if you have last-minute questions about 1 or 2 cards. And yeah. Break a leg tomorrow, and thank you for your very participative contributions and your ongoing presence in every single one of these lectures.
Mario, I've let one maybe a little bit personal question.
Yeah,
not too much.
Go.
I listened to all the presentation in the car, but of course I couldn't feel anything in the Mentimeter. But can I still do that, or
posteriori? Ruud, you can send me a list of numbers.
Oh, I don't know what all the groups were exactly.
They are in the schedule 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So like they were in order. The topics are there, and so you can basically give me like numbers from 0 to 5 if you want me to integrate them in the overall grade.
Yeah,
I'm happy to. So this is valid for anyone else that actually may have forgotten, or missed a group or something like that. I know also that, so the Mentimeter is an approximation, right? You understand that, I hope. So there are sometimes, oh, I'm voting for the wrong group, but you said 555, so that's fine, right? I think that it's all right. I mean, like as far as I saw it, as usually, it's a very peaked distribution where small differences represent generally the perception of the crowd, and I think that they give a very good sense for people receiving the grades in the other side of how people perceive the projects. But I also think that, saying one more thing, these projects that are heterogeneous, they did require like different types of efforts, and like in the presentation, we just wanted to really see how you went about it, what was the progress that you made, and that were, I think, the most important achievables for this 10-week minor, right? I think that by and large, I have no undercutting criticisms to any of you. And I don't think that you had to yourselves either, as far as the grades that you gave to each other are to speak. All right, so shall we? I wanted to actually write on screen. How do we do this? If I share the entire screen, then we can like write, we can all annotate. Can you annotate as well? So I wanted to start. Yes, no, this is for you guys. I'm loving windows here. There's windows at the back. So this is in Prague. If you were ever wondering where this building is from, it's called the Dancing House. It's pretty cool. So definitely recommend you go there. So this is like, can we draw like a heart in the shape of a brain? Maybe. So. Thank you so much, everybody. Thank you, thank you, thank you. And I hope that you have like phenomenal time and you enjoy the test tomorrow, because it will prove to you how much you have learned. And yeah, I am out of words to say. TAs, do you like why don't you say something now? Sam, Caroline, what do you think about the projects today? How do they compare with last year's projects?
Yeah, I really liked it. I was really enthusiastic about every one of them. And I think, yeah, it was kind of maybe better than last year.
Yeah, I thought so too.
Definitely consider it better than last year.
Yeah.
Yeah, and I think that they were more focused, and the goals were clearer. So they were, loads of originality.
Yeah.
And it does show that you all love brains. And I guess that everybody, oh wow, like thank you, Yime. That is way too kind. So I love you all, of course, and I'm hoping to see you repeatedly in the future, definitely next week, but also as time progresses. Come ask whatever questions you have, like also get in touch with our Vice Dean, Martin Friends, if you would like to discuss ideas with him. And remember, I mean, like, we're all open for you, any of us that has been here. So Aaron and everybody else. And Josh and Alexandra and Sadaf. And I am so convinced that, yeah, we are all looking forward to the repeated interactions between you and I. So here is not a sad face that one's for Julian and Felix, and great time, everybody. So I'm going to stop the share now. I'm actually going to press a big goodbye button, and soon more. So have a great time. And
thank you, Mario.
Thank you so much for everything, Mario.
It was great. Thank you for all the art.
Thank you.
Bye.
Bye.
Thank you. You're brilliant. Enjoy.
Good
Have a
luck.
good time.